What if the universe harbored worlds far more terrifying than any nightmare we could ever conjure in our darkest dreams? Imagine a planet where diamonds, once thought of as treasures of the earth, fall like rain from a sky alive with danger and beauty. The glittering stones rain down, a spectacle of both awe and terror, their sharp edges creating a landscape both enchanting and lethal. Or picture an infernal realm, plagued by ceaseless firestorms that tear through the atmosphere with unrelenting force, a place where survival seems not just impossible, but utterly inconceivable. Elsewhere, a towering ice giant looms on the horizon, its very breath conjuring violent hailstorms of methane, creating a cold and hostile environment where no human could endure for long. Another world, hidden in the depths of the cosmos, is shrouded in clouds of sulfuric acid, so corrosive and toxic that not even the hardiest of life forms could survive its atmosphere. Meanwhile, a tidal-locked planet bakes under the oppressive weight of extreme heat, its surface continually reshaped by the violent force of super-volcanic eruptions. Yet another world is dominated by freezing winds and swirling dark storms, its surface a frozen wasteland where nothing can escape the constant torment of nature's wrath. Then there's the ocean planet, with depths so crushing they are capable of swallowing entire ships, a watery abyss ready to engulf anything that dares venture too deep. These are but glimpses of the truly horrifying worlds where life, as we know it, cannot possibly exist. But are these just figments of our imagination, conjured from our fear of the unknown? Or could they be real? Let's take a closer look at some of the most terrifying planets and their chilling environments, beginning with the strange, mesmerizing phenomenon of diamond rain. One such planet that has been the subject of much intrigue is Neptune, the 8th planet from the Sun in our own solar system. A distant gas giant that glows with an eerie blue hue, Neptune's atmosphere is a chaotic blend of gases, including methane, which gives it its distinct color. Despite its beauty, Neptune harbors secrets that are far from pleasant. Beneath its striking surface, conditions exist that may allow for one of the most extraordinary phenomena in the universe: diamond rain. Scientists have long been fascinated by the idea that the immense pressures and frigid temperatures deep within Neptune could transform carbon into diamonds. It's a process that sounds like something out of a science fiction novel, but it is grounded in the extreme realities of the planet's harsh atmosphere. Imagine, if you will, the extreme conditions of a diamond pressure cooker. Carbon atoms under unimaginable pressure bond together in a crystalline structure that forms diamonds. These diamonds are believed to form high within Neptune's atmosphere, where the temperatures and pressures are just right. Once formed, they may fall as though they were raindrops, descending toward the planet's core, their glittering forms dancing through the atmosphere before they disappear into the depths of the gas giant. This process isn't unique to Neptune, however. Scientists believe that Saturn and Jupiter, two of the largest planets in our solar system, might also experience similar diamond rain due to their extreme atmospheres. These gas giants, with their thick atmospheres composed primarily of hydrogen and helium, also contain significant amounts of carbon. In the upper reaches of their atmospheres, carbon exists as a gas. But as you descend deeper into the planets, the pressure increases exponentially, like plunging deeper and deeper into the ocean, where the weight of the water above compresses everything beneath it. At certain depths, the pressure becomes so great that it forces the carbon atoms to bond together into solid forms, creating structures resembling diamonds. When these conditions align just right, when the temperature, pressure, and carbon concentration meet in perfect harmony, the resulting diamond particles begin to form and precipitate, much like rain forming in a cloud. Once the diamonds have formed, they may begin their descent through the thick layers of the planet's atmosphere. As they fall toward the core, they create a mesmerizing, albeit dangerous, spectacle, akin to the sight of raindrops, but instead of water, it is precious gemstones that fall from the sky, glimmering as they make their way to their final destination. This remarkable process, though awe-inspiring, highlights just how extreme the environmental conditions of these planets are, and how far beyond our own Earth they reach in terms of the materials and phenomena they produce. The diamonds that fall from these skies are not only a testament to the power of pressure and temperature, but also to the strange and bizarre conditions that govern distant worlds. To study these phenomena, scientists have turned to both laboratory experiments that simulate high-pressure environments and spectral data gathered from space probes. These studies allow them to piece together a more complete picture of how diamonds form in the atmospheres of gas giants like Neptune, Saturn, and Jupiter. By studying these distant worlds, we come to understand just how many mysteries lie hidden in the universe, waiting to be uncovered by those brave enough to reach for the stars. The phenomenon of diamond rain is but one of many strange and terrifying occurrences that might take place on planets far beyond our own. It serves as a reminder that the universe is far more complex and often more hostile than we could ever imagine. And as our technology advances and we continue to explore the cosmos, who knows what other terrifying worlds and impossible phenomena we may yet discover. The universe, it seems, is far more diverse and dangerous than we could have ever dreamed. However, in the atmospheres of gas giants like Jupiter and Saturn, conditions are remarkably different, yet also ideal for some extraordinary transformations. These massive planets, with their vast and turbulent skies, have atmospheres predominantly composed of hydrogen and helium, the two lightest elements in the universe. But scattered throughout are trace amounts of hydrocarbons, molecules made up of hydrogen and carbon. When these elements are subjected to the immense pressures found deep within these planets, conditions arise that exceed even the crushing forces present in the most extreme geological environments on Earth. At such depths, extreme pressure and intense energy, often in the form of lightning, can set off a chemical chain reaction. When energy surges through these volatile atmospheres, it can break down the hydrocarbons into their fundamental components. This process releases carbon, and under these immense pressures, this carbon can begin to crystallize into diamond-like structures. The fascinating result of this transformation is the formation of diamonds that begin to fall from the sky, like a surreal and otherworldly form of rain. Picture it, a cascade of sparkling gems descending through the dense, swirling clouds of distant worlds. Yet, unlike the liquid rain we are familiar with on Earth, the rain on these gas giants doesn't behave in the same way. The diamonds, though formed under immense pressure, wouldn't fall as droplets. Instead, due to their solid form and the unique characteristics of these extreme environments, the diamonds would likely float within the atmosphere. As gravity takes hold, they would eventually settle, gathering at deeper layers of the planet's dense, compacted atmosphere. It's a rain not of water, but of solid, shining gems scattering across vast planetary depths. This remarkable phenomenon occurs due to the unique cocktail of factors present in these planets: abundant carbon, extremely high atmospheric pressure, and energy sources like lightning. This combination creates the perfect conditions for diamond precipitation to occur. While this may sound improbable, nature, in all its vast creativity, can give rise to such unusual occurrences, demonstrating the endless possibilities of transformation in the cosmos. The idea of diamond rain was first seriously considered by astronomers after years of observing planets such as Neptune and Uranus, the so-called ice giants of our solar system. These planets, unlike Earth, are characterized by extreme pressures and low temperatures in their atmospheres, creating conditions unlike anything we experience here. Using powerful telescopes and advanced modeling techniques, astronomers carefully analyzed the light spectrums emitted by these distant worlds. What they discovered was that Neptune and Uranus, among others, contain significant amounts of methane, a compound composed of carbon and hydrogen. Methane, when subjected to the crushing pressures within the interiors of these planets, could undergo chemical reactions that break down the methane molecules. In such high-pressure environments, carbon atoms are forced to bond together in ways they typically would not on Earth, forming diamond-like structures. Researchers replicated these conditions in laboratory simulations, and the results were striking. They confirmed that carbon could, indeed, crystallize into diamonds under these extreme pressures. This observation was not only a breakthrough in understanding planetary science, but also a stepping stone toward understanding the fundamental processes that occur deep within the interiors of ice giants. The combination of observational data from space telescopes and experimental results in laboratories led astronomers to seriously consider the possibility of diamond rain occurring within the atmospheres of these distant planets. As their understanding deepened, a fascinating hypothesis began to take shape. What if, deep within the thick atmospheres of Neptune and Uranus, diamond precipitation wasn't just a theoretical notion, but an actual observable event? This idea opened up new avenues for scientific exploration. If such a phenomenon occurs, it suggests a complex and dynamic geological environment within these planets, shaped by the formation of diamonds. The process of diamond formation begins deep in the planet's atmosphere, where carbon atoms, under immense pressure, bond together to form solid diamonds. These diamonds, as they precipitate through the thick gaseous layers of the planet, could eventually settle in the planet's mantle, creating a unique geological structure. The presence of diamonds in such quantities would have profound implications for the planet's geological dynamics. For one, the accumulation of diamonds in the mantle would alter the planet's mass distribution. Unlike silicate minerals typically found in planetary mantles, diamonds have distinct physical properties. Their introduction could affect the way heat is conducted within the planet, influencing the behavior of mantle convection, the movement of molten rock beneath the surface. This, in turn, could have a direct impact on the planet's thermal evolution over time, potentially affecting its tectonic activity and even seismic behavior. The very nature of the planet's core could change, leading to new and unexpected geological features. In addition to the physical changes in the planet's interior, diamond rain could also impact the planet's electrical properties. Diamonds, known for their excellent insulation properties, could alter the way electrical currents flow through the planet's mantle. This could, in turn, affect the planet's magnetic field, creating unique interactions between the planet and the surrounding space environment. This level of dynamism in planetary geology, shaped by the precipitation of diamonds, is a reminder of the complexity and diversity of the natural forces at work across the universe. The existence of diamond rain challenges our traditional understanding of planetary formation. It compels us to reconsider the various ways nature manipulates the building blocks of the universe, crafting materials and structures that might have once seemed impossible. What once seemed like a fantastical idea, a planet where diamonds fall like rain, now appears to be a plausible, even likely phenomenon, given the right conditions. But the implications of diamond rain extend beyond just geology. If life were ever to exist on such a planet, it would face extreme challenges. Imagine an atmosphere rich in carbon, subjected to intense pressure and temperature. Under such conditions, life forms would need to adapt to the constant bombardment of solid diamond particles falling from the sky. The sheer hardness of these diamonds would create a hostile environment, one in which any organisms would need tough exteriors or protective layers to survive. The rain of diamonds could fill the air with abrasive particles, potentially harming or even destroying fragile life forms. Survival would be a relentless battle against nature's most beautiful yet most unforgiving creations. Thus, the idea of diamond rain, far from being a mere curiosity, reveals a broader and deeper truth about the universe. It is full of environments where the usual rules of biology, geology, and chemistry are upended. It highlights the incredible range of possibilities in planetary conditions, far beyond what we can imagine in our everyday world. In the cold, distant atmospheres of gas and ice giants, the very elements of life, energy, and matter are in constant flux, creating conditions both harsh and extraordinary. Imagine a world where rain doesn't fall as liquid, but as glittering diamonds, each piece a sharp, cold fragment descending from the sky. This might seem like the stuff of science fiction, yet on distant planets like Neptune and Uranus, it's a reality. The concept of diamond rain is not only awe-inspiring, but also offers a fascinating glimpse into the extreme conditions that govern the atmospheres of planets far beyond Earth's orbit. On these icy giants, the very makeup of the atmosphere is alien to our understanding, comprised primarily of hydrogen, helium, and methane. However, it is the methane with its unique chemical properties that plays a pivotal role in creating the astonishing phenomenon of diamond rain. Under the crushing pressures deep within these planets, methane undergoes a dramatic transformation. As the methane molecules are subjected to overwhelming gravitational forces, they break apart, releasing carbon atoms that are free to bond in new and extraordinary ways. These carbon atoms bond together in crystalline structures, forming diamonds that eventually precipitate, raining down toward the planet's cores. This process is a natural, yet mind-boggling reflection of the intense pressure and temperatures deep within gas giants. The temperatures in these regions can reach staggering heights, while the pressure far surpasses anything we experience here on Earth. It's a perfect storm of conditions that causes carbon to crystallize into diamonds at speeds that would make Earth's geological processes appear sluggish in comparison. While diamonds on Earth take millions of years to form deep in the mantle, here, on these distant planets, they form and fall within an incredibly short time span, almost like raindrops. The discovery of diamond rain does more than just pique scientific curiosity. It offers valuable insights into the extreme conditions that exist on other planets and could provide clues about the internal structure and composition of gas giants like Uranus and Neptune. These planets are vastly different from Earth, but through the study of their diamond-laden atmospheres, researchers can better understand the fundamental processes that occur within planetary interiors. The interaction of light and matter in such an environment, where diamond crystals might refract and scatter sunlight in unexpected ways, could also shed light on how energy flows and is distributed in the depths of these distant worlds. At first glance, the notion of life thriving in such an environment may seem inconceivable. If organisms were to exist in the presence of falling diamonds, their existence would undoubtedly depend on extraordinary adaptations. Earth's life forms, reliant on water and an atmosphere that supports breathable air, would not survive here. Instead of water, life on such planets might depend on other solvents, perhaps exotic liquids that could perform similar functions in these extreme environments. The high density caused by diamond precipitation could give rise to a thick, heavy atmosphere, potentially altering the way organisms breathe or absorb nutrients. Furthermore, the light that penetrates these atmospheres might be distorted in ways that could impact photosynthesis, the process through which plants convert light into energy. In a world where sunlight is scattered and refracted by diamonds, plant-like life would need to evolve incredibly unique systems to harness energy, potentially leading to photosynthetic processes that are far different from anything on Earth. However, life in such a world wouldn't necessarily be unthinkable. Extraordinary adaptations could emerge over time, allowing organisms to cope with the challenges of a diamond-rich environment. Still, life would look radically different from anything we're familiar with. The structures, functions, and systems we associate with life on Earth could be completely redefined. The very concept of what it means to live might change in a world that operates on a totally different set of physical and chemical rules. Beyond the potential for life, diamond rain also serves as a profound reminder of the complexity of planetary environments. The study of this phenomenon not only deepens our understanding of distant planets, but also ties back to our own planet. The processes that govern diamond formation on gas giants like Saturn and Jupiter bear similarities to the carbon cycling that happens on Earth. Extreme pressures and temperatures cause carbon atoms to crystallize in both environments, offering scientists a chance to compare and contrast the ways that carbon behaves in different settings. These insights into carbon cycles could even help refine our models of Earth's own geological and atmospheric processes. As we look deeper into the vastness of the universe, studying diamond rain offers us more than just an exotic curiosity. It's a gateway to understanding the conditions that shape worlds far beyond our own. The interplay between pressure, temperature, and atmospheric composition on other planets mirrors the processes that have influenced the formation of Earth's own features. By examining the unique ways that extreme conditions shape the environment of these gas giants, we also gain new perspectives on the history and evolution of our own planet. Moreover, the study of diamond rain could have significant implications for the search for life elsewhere in the solar system. It raises critical questions about the variety of environments that could support life, shaping our understanding of planetary formation. As scientists refine their search for habitable planets, the lessons learned from gas giants could guide them toward worlds that may harbor life, albeit in forms unlike anything we've ever imagined. The idea of obtaining diamond samples from space, particularly from gas giants like Neptune or even Saturn, brings with it a new frontier for exploration. However, the challenges of collecting and studying these diamonds are monumental. First, space is vast, and reaching the far-flung locations where these diamonds exist would require significant advancements in propulsion technology. Astronauts would need life support systems capable of sustaining them during prolonged journeys, which could last many years. Once on site, the task of extracting diamond samples from these hostile environments would require incredibly sophisticated technology. The extreme pressures and temperatures present within these planets demand equipment that can not only withstand these conditions, but also ensure that the diamonds retain their pristine structure and properties. Any research on diamonds formed in the dense atmospheres of gas giants would yield invaluable information about their formation, the processes that lead to their creation, and the potential secrets they hold about the internal workings of these planets. But the difficulty of obtaining these samples means that the tools and methods used must be cutting edge, capable of operating under the same extreme conditions that gave rise to the diamonds themselves. As humanity continues to explore the farthest reaches of space, the study of phenomena like diamond rain serves as a profound reminder of the interconnectedness of the universe. Through the study of planetary science, we uncover the shared forces and elements that shape both distant worlds and our own. Whether it's the cycle of carbon in our atmosphere or the formation of precious gems in the icy depths of a gas giant, these cosmic processes tell us more than just the story of other planets. They reveal the fundamental forces that connect all of us, from Earth to the farthest corners of the cosmos. In the vast expanse of space, diamonds are not always the sparkling gems we typically associate with luxury and elegance. Their formation, influenced by the unique conditions of distant planets and celestial bodies, can result in a strikingly different appearance. Far from being the crystalline treasures we covet, diamonds in space may be encased in ice, mixed with gases, or embedded in a variety of rocky materials. This complexity in their formation challenges our ability to recognize them, requiring scientists to develop new, specialized techniques for identifying and isolating these extraordinary specimens. The task becomes even more daunting when it comes to studying these space diamonds on Earth. Some of their most intriguing properties can only be observed under conditions that are nearly impossible to replicate in our laboratories. The very nature of their composition and formation requires unique environments that Earth simply cannot provide. Bringing samples back for analysis, therefore, becomes a significant challenge in itself. To ensure the preservation of these rare diamonds throughout their journey, scientists may need to develop specially engineered containers that shield them from Earth's atmospheric conditions which, when exposed to these delicate specimens, could easily alter or destroy their characteristics. Such missions demand not only groundbreaking technology, but also meticulous planning and a highly selective approach. Every detail must be accounted for, every possible risk considered, to maximize the chances of overcoming these profound challenges. The stakes are high because within these celestial treasures lies the potential to unlock mysteries that could forever alter our understanding of the universe. The study of space diamonds is not simply about curiosity, it's about delving into the unknown and exposing the secrets of processes far beyond our experience on Earth. One of the most exciting developments in our understanding of space comes from the discovery of diamond rain on distant planets. This phenomenon has dramatically shifted our view of the universe, challenging our long-held assumptions about planetary environments. For centuries, we imagined planets as being more or less like Earth, rocky, with atmospheres and geological processes similar to our own. However, the discovery of diamond rain on planets like Neptune and Uranus has revealed that the processes occurring on these distant worlds are vastly different from anything we could have anticipated. On these planets, the combination of extreme pressures and high temperatures forces carbon to condense into solid forms, ultimately creating structures that resemble diamonds. This revelation challenges our entire understanding of matter and its behavior under extreme conditions. Substances that we consider stable and predictable here on Earth can, under the right circumstances, transform into entirely different states, reshaping the materials we know in ways that were previously unimaginable. The implications of this discovery extend far beyond the nature of diamonds. It speaks to the incredible adaptability of matter, highlighting that the universe operates under laws that can lead to outcomes vastly different from what we expect. What was once thought to be impossible is now a reality, and scientists are rethinking everything they know about planetary formation and evolution. The discovery of diamond rain, for example, pushes us to reconsider our models of planetary atmospheres and interiors, as it suggests that other planets and moons, with conditions vastly different from Earth's, could harbor substances and materials we have never even dreamed of. The study of diamond rain also sparks broader conversations about the chemistry of life and what constitutes habitability in such extreme environments. If such processes can occur on planets far from Earth, what else might be out there? Other chemical processes, other life forms, or other materials that might allow life to flourish in unexpected ways. These questions compel us to think critically about the diverse possibilities that the universe holds and the potential for life and discovery in places that are completely foreign to our understanding. In many ways, the existence of diamond rain on other planets is a testament to the creativity of nature. It reflects the sheer complexity of the cosmos and the incredible diversity of planetary systems. Each new discovery, whether it involves diamond rain or other celestial phenomena, enriches our knowledge of the universe. It reminds us that the cosmos is not just vast, but full of surprises, many of which we are only beginning to comprehend. The exploration of these far-off worlds is a continual reminder of how little we truly know. Every new revelation, like the discovery of diamond rain, drives us further in our quest for understanding. It fuels our desire to explore the unknown, to search for new worlds, and to uncover the mysteries they hold. The universe is so much more than we can see, and each step into the unknown uncovers new questions, new challenges, and new opportunities for discovery. Far closer to home, Venus stands as one of the most extreme worlds in our solar system, often referred to as Earth's twin due to its similar size and composition. However, the similarities end there. The surface of Venus is an unrelenting inferno, dominated by a thick atmosphere composed primarily of carbon dioxide. This atmospheric composition creates a greenhouse effect so intense that it drives surface temperatures to levels comparable to the inside of a hot oven, far hotter than any place on Earth. It is on this scorching, hostile world that the phenomenon of firestorms occurs. These intense storms are fueled by a combination of the planet's extreme heat and the incredible atmospheric pressure, which is about 90 times that of Earth at sea level. In this boiling environment, sulfuric acid clouds form, contributing to a cycle that further intensifies the planet's already unbearable heat. The surface of Venus is constantly baking, unable to cool down due to the dense atmosphere. As the heat builds, massive pressure systems are generated, fueling winds and storms that rage across the planet. The combination of high temperatures, crushing atmospheric pressure, and unique chemical processes results in firestorms unlike anything we experience on Earth. These storms are not only characterized by intense volcanic activity, but also by electrical storms, all driven by the violent winds that whip across the planet at mind-boggling speeds. The planet, from a distance, may seem like a distant, beautiful world, but upon closer inspection, Venus reveals a hellish landscape where fire and fury reign supreme. Firestorms, however, are not just destructive forces. They also play a crucial role in shaping a planet's atmosphere and climate. When these intense blazes rage, they release enormous quantities of gases and particulate matter into the atmosphere. Smoke and soot, products of burning vegetation and organic material, rise high into the air, where they can travel vast distances. This not only contributes to the concentration of carbon dioxide, a potent greenhouse gas, but also disrupts the balance of other atmospheric elements that influence the climate. The particles released into the atmosphere can have a significant impact on the planet's weather patterns. Some particles can reflect or absorb sunlight, creating a shielding effect that cools the areas directly beneath or downwind of the firestorm. Meanwhile, the upper atmosphere, where these particles reside, can become significantly warmer. This dual effect, cooling in some regions and warming in others, can disrupt typical weather patterns, causing unexpected phenomena like droughts in some areas, while inducing downpours in others. This interplay of fire, heat, and chemical processes on Venus provides yet another example of how extreme conditions on distant planets can shape the environments in ways we can only begin to understand. It serves as a vivid reminder of the unpredictability of nature, urging us to reconsider everything we think we know about the planets and worlds that lie beyond our own. Firestorms, in their sheer intensity, do not merely ravage the ground below. They unleash a cascade of reactive gases, one of the most concerning being carbon monoxide. This colorless, odorless gas, when present at ground level, becomes a dangerous pollutant with the potential to disrupt both human health and the broader environment. These emissions do not exist in isolation. They interact dynamically with other atmospheric components. In this volatile exchange, smog forms, a thick, toxic haze that settles over the land. In a more intricate dance, these gases also affect cloud formation. Particles generated by the firestorms infiltrate clouds, altering their structure and chemistry in unexpected ways. As a result, weather patterns shift, most notably in the form of changes in rainfall. These disruptions are not just fleeting. They reverberate across ecosystems, affecting the availability of water and the stability of habitats. The consequences of firestorms thus extend far beyond the immediate infernos. They serve as catalysts in altering atmospheric dynamics, influencing global climate patterns. Variations in temperature and precipitation ripple through the environment, producing effects that linger for years, even decades. The balance of life on Earth, intricately woven into these delicate cycles, is fundamentally changed. Meanwhile, the role of a planet's magnetic field cannot be underestimated in shielding its atmosphere from such chaotic forces. A magnetic field acts like an invisible shield, a barrier that deflects the solar wind, a constant stream of charged particles emitted by the sun. Without this protective shield, a planet's atmosphere could gradually strip away, leaving it exposed to the harsh realities of space. The magnetic field of Earth, for instance, is a key player in maintaining the integrity of our atmosphere. It guards us against the potentially damaging effects of solar radiation, preventing the loss of atmospheric particles that would otherwise leave us vulnerable. But the influence of the magnetic field doesn't stop there. It also regulates the movement of charged particles within the atmosphere, giving rise to spectacular auroras that dance across the poles. These radiant light shows are more than just beautiful phenomena. They represent complex energy dynamics that can indirectly affect weather patterns. The stability of a planet's atmosphere is crucial in determining the occurrence and intensity of firestorms. The high heat and energy that fuel these destructive events require a delicate balance in the atmosphere, one that could easily tip into instability if the protective forces of a magnetic field are absent. A magnetic field helps preserve this balance by acting as a buffer against solar wind, preventing the loss of vital atmospheric components. Without this barrier, a planet could experience a gradual weakening of its atmosphere over time, losing key heat-trapping gases and thus destabilizing the conditions needed for firestorms to thrive. Therefore, the magnetic field plays an unexpected yet critical role in sustaining the conditions necessary for these extreme weather events. In the broader cosmic landscape, firestorms are not unique to Earth. While our planet is no stranger to extreme weather, especially when fueled by high heat and atmospheric instability, other celestial bodies also experience their own violent weather phenomena. Jupiter, for instance, provides an awe-inspiring example with its Great Red Spot, a storm that has raged for centuries. Unlike anything on Earth, this storm is driven by the intense heat and pressure of Jupiter's thick, turbulent atmosphere. The planet's composition of mostly hydrogen and helium creates unique atmospheric conditions, but the fundamental processes that generate storms, rising heat, swirling winds, and energy transfer, are eerily similar to those found in Earth's thunderstorms. The electrical activity that powers lightning on Earth mirrors the immense energy present in Jupiter's storms, which, though vastly different in scale, share similar energetic dynamics. Saturn, another giant of the solar system, also hosts massive storms, some of which form suddenly and can persist for months. These storms, though driven by a different planetary environment, demonstrate the same volatile energy patterns that we see in firestorms here on Earth. Even Mars, the cold, arid world, is not without its own version of tumultuous weather. Its dust storms, capable of engulfing the entire planet, bear striking similarities to the chaotic, swirling clouds seen in more extreme firestorm events. While the conditions on these planets may vastly differ from those on Earth, each having its own composition, temperature, and atmospheric dynamics, these planetary weather events share fundamental characteristics. They remind us that the forces at play across the solar system are not so different from those that shape the sky above us. As a planet evolves, its volatile environment is shaped by millions of years of geological and atmospheric processes. The birth of a planet begins with the aggregation of dust and gas in space. This primordial collection of material generates intense heat, setting the stage for geological activity that will define the planet's future. Volcanic eruptions, a fundamental driver of atmospheric change, release gases into the environment, gases that interact with the atmosphere and trigger changes in weather patterns. As the planet cools, a crust begins to form, but this surface is anything but uniform. It is divided into tectonic plates, which float atop the molten mantle below. Over time, these plates shift, collide, and drift apart, causing earthquakes and giving rise to mountain ranges. The constant movement of these plates ensures that the planet's surface is never static, continually reshaped by geological forces. A planet's atmosphere undergoes its own evolution. In the early stages, it may be thick with toxic gases such as carbon dioxide and sulfur, much like Earth's young atmosphere. Volcanic activity, ever present on a planet still in the throes of development, contributes to this volatile mix, releasing gases that further interact with the environment. Over time, these atmospheric conditions shift. Weather patterns emerge and evolve, and with them, the planet's climate. The combined effects of volcanic activity, tectonic movements, and atmospheric changes foster a dynamic environment in which firestorms can emerge. As these storms grow more intense, they are fueled by the very geological processes that shape the planet, completing the cycle of volatility that defines these extreme weather events. Thus, the evolution of a planet is a slow yet inexorable process, one that intertwines geological and atmospheric forces to create environments capable of sustaining firestorms. The interplay of these elements is not only a testament to the dynamic forces at work within a planet's system, but also a reminder of the raw power and unpredictability of nature, both on Earth and beyond. External events, such as asteroid impacts, play a pivotal role in shaping a planet's environment. These catastrophic events have the potential to trigger dramatic shifts in the climate, which can lead to long-lasting changes in the atmosphere and the balance of gases that sustain life. When an asteroid collides with a planet, the impact can be far-reaching, disrupting not just the atmosphere, but also triggering widespread volcanic activity. This eruption of volcanoes injects additional heat and pressure into the planet's crust, compounding the environmental chaos. The presence of these forces can leave a profound and lasting imprint on the planet, altering its landscape and ecosystems in unexpected ways. Furthermore, the movement of water is another critical factor that determines the stability of a planet's environment. A planet rich in water, especially vast oceans or large bodies of liquid, engages in a complex interaction with the crust beneath. This interaction can lead to phenomena like erosion, which wears down rock formations, and sediment deposition, which reshapes the planet's surface. As water dissolves minerals, it transports them across various regions, playing an essential role in the planet's chemical cycles. This process adds an extra layer of volatility, making the environment more dynamic and prone to shifts that could radically alter the course of a planet's geological evolution. Together, the volatile environment of a planet arises from a series of interconnected formative processes. The heat from its formation, ongoing tectonic movements beneath the surface, ever-changing atmospheric conditions, external cosmic impacts, and the transformative power of water all converge to create an environment in constant flux. These elements are not separate forces, but a blend of forces that keep the landscape alive with geological activity. It is within this context of continuous transformation that the planet's future unfolds, shaped by both the internal and external forces that shape its fate. Picture for a moment a desolate landscape ravaged by the unforgiving force of a firestorm. The sky above is swallowed by swirling clouds of ash and smoke, casting a thick, oppressive shadow over the barren land below. The air hangs heavy, thick with the acrid scent of burning materials, while fierce flames leap across the surface, devouring everything in their path. The once solid earth now lies cracked and scorched, blistered by extreme temperatures that threaten to burn anything that dares to touch it. Glowing patches of molten lava break through jagged rock formations, their intense heat casting an otherworldly glow against the blackened surroundings. The towering rock structures, like silent sentinels, glow red-hot from the searing temperature, adding to the alien landscape that unfolds before you. In the distance, rivers of molten lava flow like liquid fire, carving their way through the terrain, casting an eerie light upon everything in their path. The winds howl through the landscape, whipping up embers and debris, and every so often a fierce burst of flame erupts from the ground, sending showers of sparks into the air. Amidst this chaos, the sounds are deafening. The roar of flames, the crackle of burning materials, and the occasional rumble of the ground beneath, shifting under the intense heat. Survival in such an environment seems nearly impossible. The ever-changing conditions make it hostile at every turn, with the landscape itself constantly reshaping as the forces of fire and heat consume the land. Yet, in the face of this destruction, the land transforms, creating unique geological features over time. What seems like an inhospitable wasteland is in fact a fertile ground for renewal, where new life can emerge from the ashes, shaping a harsh beauty from the destruction. It is a stunning reminder that even in the most hostile environments, resilience is not only possible, but essential. The study of such intense and continuous storm systems, whether on Earth or beyond, involves the application of cutting-edge technology and complex modeling techniques. Satellites orbiting high above the planet serve as the first line of defense, capturing massive amounts of data. These satellites monitor storms in various wavelengths of light, allowing scientists to peer beyond the limits of human vision. By observing cloud formations, lightning strikes, and precipitation patterns, they can track the development of storms and gain insight into their behavior over time. But satellites alone do not provide the full picture. Ground-based weather stations are critical in capturing localized data. These stations, strategically placed across the globe, measure crucial variables like temperature, humidity, and wind speed at different altitudes. This real-time data helps paint a more accurate picture of what is happening on the surface, adding another layer of depth to the understanding of storm systems. Once the data is collected, scientists turn to computer models, highly sophisticated simulations of the atmosphere based on the fundamental laws of physics. By inputting real-time data into these models, researchers can simulate how storms might evolve, interact, and intensify over time. These models take into account the interactions between various atmospheric layers, geographic features, and other factors that influence storm behavior. As computational power increases, more advanced tools, such as supercomputers, allow for simulations with greater accuracy, incorporating larger data sets and more precise resolution. Machine learning also plays an increasingly important role in storm prediction. By analyzing historical storm data, machine learning algorithms can identify patterns and correlations that may not be immediately obvious. These systems improve predictive capabilities by targeting specific regions that are more likely to experience severe weather, allowing scientists to issue more accurate warnings and better prepare communities. This holistic approach, combining satellite imagery, ground-based data, advanced computer models, and machine learning, marks a significant step forward in understanding and predicting intense storm systems. Such advancements not only help predict the weather with greater accuracy, but also allow for better preparedness, helping mitigate the impact on agriculture, ecosystems, and human populations. When considering space exploration and missions to distant planets, the array of potential hazards multiplies. Each planet presents its own set of challenges that could significantly impact the safety and success of a mission. One of the most immediate concerns is the extreme temperature variations that many planets experience. Some worlds are scorched by the heat of their sun, while others plunge into freezing cold during the night. These temperature extremes can place a great deal of strain on equipment, damaging sensitive instruments or rendering them inoperable entirely. Atmospheric conditions also present challenges that cannot be ignored. Thick clouds may obscure visibility, making it nearly impossible to accurately navigate or conduct surface operations. High winds can complicate landing procedures, increasing the risk of damage or failure. Furthermore, the presence of corrosive gases in a planet's atmosphere can slowly degrade equipment over time, presenting an additional layer of complexity for mission planners. The surface conditions of planets can be equally, if not more, dangerous. Uneven terrain, filled with deep craters and towering mountains, can make landing or maneuvering a rover difficult, if not impossible. Vast plains of dust can also hinder visibility and the ability to navigate effectively. The risk of landing on an unstable surface is ever present, with the possibility of tipping over or getting stuck, making it difficult to continue exploring the planet's surface. Radiation exposure is another serious concern. Space missions, whether manned or unmanned, must contend with high levels of cosmic radiation, far more intense than anything we experience here on Earth. This radiation can pose significant risks to both astronauts and electronic instruments, requiring advanced shielding or other protective measures to ensure the safety of the mission and the integrity of the equipment. This makes it clear that planning and executing successful space missions requires a thorough understanding of a planet's unique conditions and the careful consideration of all potential hazards that might arise. The uncertainties surrounding a planet's environment necessitate thorough, meticulous planning, particularly when it comes to interplanetary missions. From the moment a mission is conceptualized, it becomes clear that unpredictable challenges must be addressed head-on. One of the most significant hurdles is the possibility of violent dust storms sweeping across the planet's surface. These storms could drastically reduce visibility, potentially blocking vital communication with Earth, and even interfere with the mission's operations. Such environmental challenges demand extensive forethought and preparation. It is critical to design comprehensive strategies capable of mitigating these potential hazards, ensuring that the mission's success is not left to chance. Moreover, firestorms, especially those on planets like Mars, pose unique and serious implications, not only for the possibility of sustaining life, but also for the future availability of essential resources. When thinking about firestorms in a planetary context, we typically envision fierce dust storms or extreme wildfires, phenomena that could drastically reshape the environment. A firestorm in this setting is more than just a natural disaster. It signals an environment that can swing between extreme conditions. Similar to the wildfires we experience on Earth, these events could involve extreme fluctuations in temperature, creating an atmosphere that is inhospitable to life as we know it. Many organisms rely on relatively stable temperatures and atmospheric conditions to survive, making such drastic shifts incredibly dangerous. In the wake of firestorms, entire ecosystems could be obliterated, habitats destroyed, and the organisms that depend on them driven to extinction. However, there's also a silver lining. Despite the destruction, firestorms can play an essential role in the regeneration of ecosystems. In many earthly environments, fire is a natural process that clears old, dead vegetation, making way for new growth. This cycle of destruction and renewal could similarly allow life to regenerate on other planets, fostering the emergence of diverse species that can adapt to a temporarily altered landscape. Over time, new plants and animals might thrive in these transformed environments, using the opportunity to establish themselves in the wake of previous chaos. From a resource perspective, firestorms could also unveil hidden treasures beneath the planet's surface. On Mars, for example, the intensity of such storms could expose subsurface ice or mineral deposits that may be crucial for future human missions. Water ice, uncovered by these fiery events, could serve as a critical resource for sustaining life and supporting future exploration. As humanity plans for long-term colonization, such discoveries could be the key to survival, enabling astronauts to use these resources for water, fuel, and even life support systems. While the immediate aftermath of firestorms might be catastrophic, their longer-term effects offer unique opportunities for scientific discovery. These powerful forces could reveal new possibilities for exploration and open up unforeseen pathways for human settlement on distant planets. By studying the intricate dynamics between destructive forces like firestorms and the resilience of ecosystems, scientists can better understand the delicate balance of life and resources on other worlds. This knowledge could pave the way for more sustainable, adaptable strategies when venturing into unknown territories. A particularly fascinating aspect of planetary firestorms can be found on Jupiter, where storms of a magnitude and duration that seem impossible by Earth standards unfold. For instance, Jupiter's Great Red Spot, a massive storm that has persisted for more than 300 years, demonstrates a remarkable stability that has baffled scientists for centuries. Unlike the brief duration of a typical Earth hurricane, which may last only a few days or weeks, Jupiter's firestorms can endure for centuries, raising questions about the underlying forces at play. The Great Red Spot, as well as other similar storms on Jupiter, exhibit a persistence and resilience that defy our understanding of atmospheric dynamics. Moreover, these storms are not static. They interact with one another, often merging, spinning off new storms, or suddenly changing direction. Such unpredictability adds a layer of complexity to weather patterns that was previously unimagined. It's as if the atmosphere on Jupiter is engaged in a constant, chaotic dance of turbulent currents, continuously shifting and evolving in ways that challenge the scientific community's understanding of planetary weather. The sheer scale of these firestorms on Jupiter is another astonishing aspect. These storms can be so massive that they could easily engulf entire planets. The ferocity of these storms, with winds that exceed the speed of sound, contributes to their overwhelming power. The energy involved is mind-boggling, and it challenges our fundamental understanding of physics. Such intensity forces us to reconsider our assumptions about weather phenomena, highlighting how vastly different celestial environments can produce weather systems far beyond anything found on Earth. These planetary firestorms speak to the dynamic and ever-changing nature of the universe. The fact that such colossal storms can persist for centuries challenges our understanding of planetary science and weather systems. As we venture deeper into space exploration, these storms continue to captivate our imagination, offering new mysteries to unravel. What other secrets might be hidden within the atmospheres of distant worlds? What can we learn from these raging firestorms that might expand our understanding of planetary science and even the possibility of life elsewhere in the universe? Turning our gaze to another extreme example, Neptune, an icy world far from the sun, reveals yet another aspect of planetary firestorms that is both beautiful and terrifying. Known for its intense methane hailstorms, Neptune presents one of the most fascinating, if inhospitable, environments in the solar system. At first glance, Neptune seems serene, its deep blue hue offering an illusion of calmness. Yet beneath this tranquil exterior lies a violent, dynamic atmosphere powered by internal heat rather than solar energy. Composed mostly of hydrogen, helium, and a significant amount of methane, Neptune's atmosphere is a hotbed of chaotic weather patterns. The methane in Neptune's atmosphere not only contributes to the planet's striking appearance, but also plays a crucial role in driving its weather phenomena. As the internal heat of the planet interacts with the methane, it creates conditions for intense storms, particularly those involving frozen methane hail. These hailstorms are unlike anything experienced on Earth, as the methane condenses and freezes into icy formations that fall to the planet's surface with shocking violence. The hailstones, driven by the planet's ferocious winds, can deliver an incredibly cold, forceful impact, further complicating the planet's already extreme environment. The formation of these hailstorms is driven by convection, the process in which warm, moist air rises quickly through the atmosphere, encountering cooler air higher up. As this warm air cools, water vapor condenses and freezes, forming tiny ice crystals. In storms with particularly strong updrafts, these ice pellets are lifted repeatedly through the atmosphere, growing larger as they gain additional layers of ice. When the hailstones finally become too heavy for the updrafts to support, they fall violently to the surface, their size directly correlated to the strength of the storm's updrafts. The size and intensity of hailstones on Neptune can be awe-inspiring, with the largest occurring during particularly violent storms. As with hailstorms on Earth, the severity of the storm and the amount of moisture available in the atmosphere determine the size of the hail. In Neptune's case, the conditions are so extreme that the hailstones could be much larger and more destructive than anything we experience on Earth. The planet's weather system, shaped by its internal heat and dynamic atmospheric processes, offers a powerful reminder of how varied and unpredictable the weather can be in our solar system. The atmosphere plays a crucial role in shaping the intensity and behavior of storms, and environmental factors like temperature and humidity are particularly influential in determining the strength of a storm. The combination of strong updrafts, an abundance of moisture, and favorable atmospheric conditions sets the stage for storms that can bring severe weather, including hail. The formation of hailstones, which are frozen raindrops, occurs under conditions where the updrafts in the storm are strong enough to carry water droplets high into the atmosphere, where they freeze and accumulate layers of ice. As these hailstones grow, they eventually fall to the Earth's surface, sometimes with enough force and size to cause significant damage. But hailstorms are not limited to our planet. They are also observed in environments far beyond Earth. One of the most fascinating and extraordinary instances of hailstorms occurs in the extreme, frigid environments of other planets, such as Saturn's moon, Titan. On Titan, the atmospheric conditions are very different from those of Earth, yet the processes that drive storms bear a resemblance to those we are familiar with. The atmosphere of Titan is dense and composed primarily of nitrogen and methane, rather than water vapor, which is the main ingredient for weather patterns here on Earth. Titan's methane-rich atmosphere supports storms and weather patterns, but with a striking twist. Instead of water, it is methane, the primary hydrocarbon in Titan's atmosphere that fuels the storm system. The scale of these storms is colossal, with methane precipitation in the form of liquid droplets that can grow large enough to fall to the ground, similar to hailstones. The landscape of Titan, which is covered in icy surfaces, is dramatically reshaped by these methane hailstorms. The force with which the methane droplets strike Titan's surface releases vast amounts of energy, enough to erode the surface and carve out new features, much like how water-driven erosion can shape the landscapes of Earth. The erosion caused by these storms can even form river-like channels in Titan's icy crust, leading to the creation of organic-rich wetlands that evolve over long timescales. These processes of erosion and landscape transformation on Titan are linked to the moon's complex geology, and the implications of these methane hailstorms extend far beyond just surface changes. They offer insight into the dynamic interplay between the atmosphere and the planet's geology, creating a fascinating environment that offers a window into planetary science. The sheer scale of these storms and the powerful impact they have on the surface highlights how weather systems on other planets can operate on a grand scale, sometimes leading to profound alterations in the planet's topography and ecosystem. Over time, the repetitive cycle of methane clouds forming, raining down, and reshaping Titan's icy surface sustains a dynamic and ever-changing environment. This makes Titan a subject of intense interest for scientists who study planetary atmospheres and the potential for weather systems beyond Earth. Methane, the key player in these storms, also plays a critical role in shaping the climate and weather systems of Titan. On Earth, methane is a potent greenhouse gas, much more effective at trapping heat in the atmosphere than carbon dioxide. This means that when methane is present in significant quantities, it acts like a thick, insulating blanket around the planet, trapping heat and raising temperatures. On Earth, methane is released through natural sources, such as wetlands and permafrost, as well as through human activities like fossil fuel extraction. Once methane enters the atmosphere, it can accelerate global warming, creating a feedback loop that leads to higher temperatures, more intense storms, and extreme weather events like hurricanes, heavy rainfall, and drought. To imagine this effect, think of the Earth's atmosphere as a blanket that keeps heat close to the surface, ensuring that the planet maintains a temperate climate. When methane enters the atmosphere, it thickens this blanket, trapping more heat and raising global temperatures. As the atmosphere heats up, weather patterns become more unpredictable. The hydrological cycle, how water moves through the atmosphere, condenses, and falls as precipitation, becomes destabilized, leading to a mix of increased evaporation and intense rainfall in some regions, while others experience dry spells. This disruption affects ecosystems, agriculture, and water resources as extreme weather events impact crop yields and the health of natural habitats. Moreover, as global temperatures rise, reservoirs of methane that are trapped in ice, permafrost, and wetlands are released into the atmosphere, creating a dangerous feedback loop. The more methane that is released, the more temperatures rise, and this cycle exacerbates climate change. The management of methane emissions is crucial in the battle against global warming because reducing methane levels could help stabilize the climate and mitigate the extreme weather events that are becoming more frequent. Understanding the dynamics of methane in Earth's atmosphere is key to preventing the worst outcomes of climate change. The role of methane in weather systems is also seen beyond Earth, particularly on gas giants like Jupiter. Jupiter's atmosphere, filled with hydrogen, helium, and traces of methane, presents an entirely different environment compared to Earth. While Earth's hailstorms form when water droplets are carried up into the cold upper atmosphere, where they freeze and fall as hail, Jupiter's storms take on a unique form due to the planet's immense atmospheric pressure and turbulent weather systems. On Jupiter, the powerful updrafts created by the planet's extreme weather systems can lift water and ammonia droplets to great heights, where they freeze into hailstones that fall back to the surface. However, the composition of Jupiter's hailstones is quite different from Earth's. While Earth's hailstones are typically composed of water ice, Jupiter's can include ammonia and methane, gases that are prevalent in the planet's atmosphere. These particles form in Jupiter's high-energy environment, where the strong winds and turbulence allow hailstones to grow to enormous sizes. While hailstones on Earth might reach the size of golf balls in severe storms, those on Jupiter can be as large as baseballs or even larger, depending on the strength of the updrafts. The size and frequency of these extraterrestrial hailstorms make them a fascinating subject of study, as they are not only more extreme in size, but also in scale. Jupiter's storms span vast regions of the planet, unlike the localized storms we see on Earth. The gas giant's rapid rotation and thick, turbulent atmosphere allow its storms to cover enormous distances, creating a pattern of widespread atmospheric disturbance. These storms can last much longer than the storms on Earth and often grow more intense as they evolve. Jupiter's extreme weather systems provide insight into the mechanisms of planetary weather, highlighting the stark differences between Earth's relatively mild climate and the ferocious, tempestuous weather of gas giants. In the end, whether it's the methane hailstorms of Titan or the powerful storms on Jupiter, these phenomena expand our understanding of how weather systems can develop and evolve on planets far beyond Earth. The study of these storms gives us a glimpse into the complexity and dynamism of planetary atmospheres, helping us unravel the mysteries of weather patterns in the broader universe. The atmospheric conditions between Earth and Jupiter are starkly different, and this contrast significantly shapes the characteristics of weather phenomena on both planets. On Earth, the clouds that blanket our sky are primarily composed of water vapor, a compound that plays a crucial role in weather systems. Jupiter, however, presents a much more complex picture. Its clouds are made up of a diverse mixture of gases, including ammonia and water vapor, which create a distinct set of atmospheric dynamics. This difference in composition not only influences the cloud structures, but also dramatically alters the processes behind hail formation, especially when compared to Earth's weather systems. While hailstorms on Earth and other planets, such as Jupiter, may share some foundational processes in their formation, the resulting phenomena diverge significantly in composition, size, frequency, and the underlying atmospheric conditions. These variations are essential to understanding the intricate dynamics of weather across the universe. By studying these differences and similarities, scientists can glean insights into the forces that drive weather systems on planets vastly different from our own, providing us with a broader understanding of planetary atmospheres and the way they influence life, geology, and climate. To investigate these extreme weather phenomena on distant worlds, Scientists employ an array of sophisticated technologies that enable them to study planets and moons far beyond our reach. A critical tool in this exploration is the space-based observatory. These observatories capture data across a range of wavelengths, such as infrared and radio, providing invaluable insight into the atmospheric composition of distant worlds. Through these observations, scientists can visualize temperature variations, atmospheric patterns, and even storm systems on planets like Jupiter or distant moons, offering a remote yet powerful glimpse into their weather systems. Telescopes equipped with specialized instruments further enhance these observations, enabling researchers to analyze the composition of a planet's atmosphere by studying the light that passes through it or reflects off its surface. This method of analysis allows scientists to identify the gases and particles present in the atmosphere, shedding light on weather patterns and environmental stability. Understanding these details is crucial for constructing an accurate picture of the planet's atmospheric behavior and potential for supporting life. In addition to telescopes, spacecraft are outfitted with weather monitoring instruments that measure atmospheric pressure, temperature, and wind speeds. These probes, often sent to study planets such as Mars or the gas giants like Jupiter, collect first-hand data that help to unravel the mysteries of weather phenomena. For example, the study of dust storms on Mars or the swirling hurricanes on Jupiter offers a glimpse into how weather patterns can manifest in radically different environments. The information gathered by these spacecraft can provide key insights into the processes that drive extreme weather events, both on Earth and on other planets. Computer simulations also play a pivotal role in planetary weather research. These simulations allow scientists to build models of planetary atmospheres by inputting the data gathered from telescopic observations and spacecraft measurements. With this data, scientists can forecast weather patterns, explaining the physical processes that give rise to these events. By combining remote observation, direct measurement, and sophisticated computer modeling, scientists are able to develop a dynamic understanding of how extreme weather behaves on distant worlds. These advanced technologies enable scientists to create a detailed picture of how extreme weather phenomena function in alien environments. For instance, methane hailstorms observed on moons like Titan reveal how distinct environmental conditions can lead to the formation of unique weather patterns. Titan, Saturn's largest moon, has a thick atmosphere primarily composed of methane, a gas that exists in various forms, gas, liquid, and solid, depending on the temperature and pressure. In Titan's frigid environment, methane can condense into liquid pools and lakes, which, under the right conditions, may freeze and fall as solid methane hail. The formation of methane hail on Titan is not just a curious anomaly. It provides valuable insights into the hydrocarbon cycles of the moon. These storms reveal how energy moves through Titan's atmosphere and how chemical reactions occur when methane interacts with other atmospheric molecules. The study of such storms is crucial, not only for understanding Titan's unique atmospheric chemistry, but also for examining prebiotic conditions that could potentially foster life. Understanding the chemical interactions that form these compounds could have far-reaching implications, shedding light on the potential for life in other parts of the universe. Furthermore, methane hailstorms also offer valuable analogies for understanding weather patterns here on Earth. By observing how different planetary bodies exhibit diverse forms of atmospheric behavior, scientists can learn about the fundamental processes that govern weather systems, helping us appreciate the complexity and diversity of planetary atmospheres. These studies offer crucial insights into how unique environments might support life, offering clues to scientists as they search for habitable worlds beyond our solar system. The impact of methane hail on Titan's surface could be profound, altering the geological landscape in ways that differ from anything we experience on Earth. If methane were to freeze and fall as hail, the resulting impacts could create craters, depressions, or even erode rocks over time, leading to a gradual reshaping of the surface. The cold nature of methane means that, upon impact, it could interact with other substances like rock or ice, triggering a variety of physical and chemical reactions. These interactions could change the material properties of the surfaces they impact, potentially creating new geological features. For example, repeated impacts could leave behind methane residue or ice, layering over time to form structures unlike anything seen on Earth. Such interactions could have a profound effect on the Moon's ecosystem and hydrological systems. The release of methane and other materials during impacts could contribute to the formation of unusual geological formations, or even create new habitats that might support different forms of life. If methane transformed into liquid in warmer post-impact environments, it could function as a solvent, breaking down minerals in a way similar to water, but with entirely distinct chemical properties. While the concept of methane hail remains theoretical, its potential effects on Titan's surface and atmosphere offer fascinating possibilities for planetary science. As scientists explore these ideas further, they continue to broaden our understanding of planetary processes beyond Earth. These studies spark curiosity about the diversity of life forms and landscapes that may exist elsewhere in our universe, challenging our preconceived notions about the conditions necessary for life to thrive. The potential for harvesting methane hail presents yet another avenue of exploration, opening a window into both the scientific and practical possibilities that this phenomenon offers. In regions of our solar system like Titan, methane exists not only as a gas, but also in solid forms, including hailstones. These frozen methane droplets, though vastly different from the water ice we are familiar with on Earth, could provide valuable data for understanding extraterrestrial weather systems and the atmospheres of distant moons. By studying these methane hailstones, scientists could gain deeper insights into the conditions under which they form and their role in shaping the climate and environment of Titan. In sum, the study of extreme weather phenomena, such as methane hailstorms, deepens our understanding of planetary atmospheres and the chemical processes that govern them. It challenges our assumptions about how weather systems work and provides us with a fresh perspective on the forces that shape distant worlds. As technology continues to advance, our ability to explore these phenomena will only grow, offering ever-expanding possibilities for understanding the complexities of the universe and the potential for life on other planets. Methane, a simple molecule composed of one carbon atom and 4 hydrogen atoms, holds a surprising level of value beyond our planet. On Earth, it's known as a significant source of energy, used extensively for heating, electricity generation, and various industrial applications. However, its potential stretches far beyond the atmosphere of our home planet. In the context of space exploration, methane could become a key resource for future missions. If scientists were to develop ways to efficiently collect and use methane found in space, such as from distant moons or comets, it could be harnessed as a fuel source for spacecraft, reducing the need to transport fuel from Earth. This could significantly improve the efficiency and sustainability of long-duration space missions, where carrying vast amounts of fuel from our planet is impractical. Moreover, methane is not just a source of energy. It's also a fundamental building block for more complex organic molecules. In astrobiology, this characteristic makes methane an exciting avenue for exploration. If life exists or existed on other planets or moons, methane could play a pivotal role in the development of those life forms. By studying how methane interacts with other chemicals in distant environments, scientists could gain insights into how life could develop or even thrive in conditions vastly different from those on Earth. Such research might open doors to understanding the biochemistry of alien organisms, should they exist. The concept of harvesting methane in space is still largely theoretical, but the idea underscores the remarkable ingenuity required for space exploration. It highlights the importance of developing advanced technologies that can extract and use extraterrestrial resources to sustain human presence beyond Earth. With each step, we inch closer to transforming what were once dreams of the future into practical realities that could shape the logistics of human endeavors in space. The implications of harnessing methane from asteroids, moons, or even distant planets are profound, not just for science, but for the future of interplanetary travel. As we consider where life might exist beyond Earth, icy moons such as Europa and Enceladus offer tantalizing possibilities. These moons, orbiting the gas giants Jupiter and Saturn, are enshrouded by thick layers of ice that conceal vast, hidden oceans beneath their surfaces. Scientists have speculated that these moons may harbor environments capable of supporting life, despite their frigid and inhospitable surface conditions. The potential for life to thrive in these remote, frozen oceans challenges everything we know about biology, especially when considering the fact that these moons are located far from the warmth of the sun. In these icy environments, it's conceivable that life forms could rely on chemosynthesis, using chemical reactions rather than sunlight to produce energy. On Earth, deep-sea organisms thrive in places like hydrothermal vents, where they harness energy from minerals and chemicals released by the Earth's crust. Similarly, microbes in the oceans of Europa or Enceladus might rely on chemical reactions between water and minerals to generate the energy necessary for life. The harsh conditions on these moons could even give rise to life forms that are fundamentally different from any life on Earth, adapted to survive extreme cold, crushing pressures, and radiation from space. The concept of extremophiles, organisms that flourish in extreme environments, already exists on Earth. From organisms living in the boiling waters of hot springs to those thriving deep in the abyssal trenches of the oceans, Earth's extremophiles demonstrate that life is capable of thriving in conditions once thought too extreme for survival. These resilient organisms have evolved to withstand pressures, temperatures, and chemical environments that would be lethal to most other life forms. This resilience suggests that life could similarly adapt to the extreme conditions found in other parts of the solar system. Consider, for example, the potential for organisms on icy moons to develop unique biochemical mechanisms, such as antifreeze proteins that prevent their bodily fluids from freezing. They might also possess cellular structures designed to withstand the crushing pressures and intense radiation beneath the icy surfaces. These possibilities challenge our understanding of the limits of life, sparking an exciting line of research in astrobiology. If life can evolve on Earth in such extreme environments, who's to say it can't do the same on distant celestial bodies? The ongoing study of these icy worlds continues to fuel curiosity, with space missions dedicated to exploring Europa, Enceladus, and other potentially habitable moons. In many ways, the potential discovery of alien life, or at least the conditions that could support life, offers one of the most thrilling prospects for the future of space exploration. If life can exist on distant moons in our solar system, it suggests that similar forms could exist elsewhere in the vast expanse of the universe. But if these alien environments hold such promise for discovering new forms of life, what about planets that seem completely inhospitable? Take Venus, for instance, a planet renowned for its dense, toxic clouds of sulfuric acid. Its thick atmosphere forms a thick veil, creating an atmosphere of mystery and danger. The clouds of Venus are not ordinary, water-laden clouds. They're composed of sulfuric acid droplets combined with other gases like carbon dioxide. This makes Venus's atmosphere one of the most hostile in our solar system. These clouds are the product of complex chemical reactions. Sulfur dioxide, an abundant gas in Venus' atmosphere, reacts with sunlight, triggering a series of reactions that lead to the formation of sulfuric acid. The process is accelerated by Venus's extreme surface temperatures and pressure, conditions so harsh that they would melt lead. As the sulfuric acid droplets gather, they form thick, swirling layers of clouds that completely obscure the surface of the planet. These toxic clouds reflect much of the sunlight, further contributing to the runaway greenhouse effect that defines Venus. In this runaway greenhouse scenario, carbon dioxide traps heat within the atmosphere, causing surface temperatures to soar to levels high enough to melt metal. This creates a feedback loop where the trapped heat only exacerbates the already extreme conditions. Venus, with its swirling clouds of sulfuric acid and scorching surface temperatures, stands as one of the most inhospitable worlds in our solar system. The very atmosphere that makes Venus so deadly also serves as a profound reminder of the delicate balance required for life to thrive. The thick sulfuric clouds of Venus are not just a toxic feature of the planet. They are a defining characteristic of its hostile atmosphere. Understanding the dynamics of such environments, how they form, and how they interact with the surface can offer critical insights into planetary science. They may even give us clues about the history of Venus itself, how it evolved into such an extreme environment, and whether it ever had the potential to support life. While Venus today may be a toxic, scorched world, the possibility remains that there was a time when its environment was much more temperate and life may have had a chance to take hold. In the search for life beyond Earth, planets like Venus and moons like Europa and Enceladus offer striking contrasts, some of the harshest, most unforgiving places in the solar system, and yet, within these extreme environments lies the potential for life's surprising adaptability. Moreover, Venus's atmosphere is often characterized as a textbook example of a runaway greenhouse effect, a phenomenon so extreme that it has transformed the planet into one of the most inhospitable worlds in the solar system. This relentless heat-trapping process is driven by an exceptionally dense atmosphere, dominated by carbon dioxide, a gas known for its ability to trap heat with remarkable efficiency. The result? Surface temperatures soaring high enough to melt lead, easily surpassing the hottest places on Earth, despite Venus being located at a distance from the Sun that might suggest otherwise. This heat doesn't simply warm the surface. It accelerates the cloud formation process, compounding the planet's brutal environmental conditions. As these thick, toxic clouds spiral around Venus, they create a stunning, though perilous, visual spectacle. From a distance, the swirling mass of clouds looks almost beautiful, but this appearance belies the lethal conditions they conceal. The clouds are not just there to decorate the planet's atmosphere. They play a critical role in the planet's extreme climate dynamics, reinforcing Venus's reputation as one of the most inhospitable places in our solar system. One of the key elements in Venus's atmospheric composition is sulfuric acid. This compound plays a central role in shaping the planet's weather patterns, much like it does on other planets in our solar system, but its impact is especially pronounced on Venus. Picture the atmosphere thick and heavy, with clouds laden with droplets of sulfuric acid. These clouds have the ability to reflect sunlight, causing it to bounce back into space, which paradoxically serves to enhance the greenhouse effect, trapping even more heat within the planet's atmosphere. As a result, surface temperatures on Venus reach levels far higher than one might expect given its distance from the Sun, creating a truly extreme and alien environment. But the role of sulfuric acid doesn't stop with temperature regulation, and these clouds are also responsible for creating the most extreme weather phenomena on Venus. As they evolve, they can lead to a kind of precipitation that is not seen on Earth: acid rain. This acid rain, though vastly different from Earth's rainfall, plays a major part in shaping the surface of Venus. It contributes to a continuous cycle of erosion and chemical reactions that alter the landscape in ways that are still not fully understood by scientists. In addition to its impact on temperature and weather, the sulfuric acid clouds of Venus also shape the planet's atmospheric circulation. These clouds can give rise to towering storm systems, which, when combined with the intense heat, create a highly dynamic yet stable climate. These weather systems create a peculiar paradox, where the atmosphere is thick and persistent, yet constantly evolving with the formation of storms that dramatically alter local conditions. The presence of sulfuric acid, therefore, transforms Venus into a world with a climate that is both incredibly stable and unpredictably dynamic. The long-term temperature regulation, combined with the perpetually shifting weather patterns, makes Venus a place where life, as we understand it, could never exist. It is a world where heat and toxic clouds dictate the rules, creating an environment that is both hostile and fascinating in equal measure. The emergence of toxic clouds, especially those composed of harmful gases and particulates, can have profound consequences not just on the planet's surface conditions, but also on any potential ecosystem that might attempt to exist there. Such clouds are capable of disrupting any kind of biological processes, as they directly affect air quality. For any organisms that might exist in such a toxic atmosphere, breathing becomes a major challenge. The inhalation of these noxious gases could cause severe health problems, hinder reproduction, and ultimately lead to population decline. This would be true for both plant and animal life, should such life ever be able to survive in such a world. For plants, the situation is equally dire. Toxic clouds, especially those laden with sulfuric acid, have the potential to hinder the vital process of photosynthesis, the process through which plants convert sunlight into energy. Without access to sunlight, plants on Venus would be unable to produce the food needed for survival, leading to their rapid decline. As plants struggle to survive, herbivores that depend on them would also face extinction, leading to a ripple effect throughout the entire food web. The intricate relationships between species would be torn apart, creating a devastating disruption to any potential ecosystem. Furthermore, as acid rain falls from Venus's atmosphere, it carries with it these toxic elements, which seep into the planet's soil and water sources. This not only contaminates the ground, but also renders the planet's environment even more hostile to any form of life. With the soil rendered inhospitable, the types of plants that might have been able to grow in that environment would be limited, shifting the balance of the planet's potential habitats and causing further alterations to the species that might have called it home. But the dangers don't stop on land. Toxic clouds can also threaten the planet's aquatic ecosystems, should they exist. The acid rain could wash harmful substances into any rivers or lakes, creating an environment where fish and other aquatic organisms struggle to survive. As contaminated water sources spread, they could lead to mass die-offs of fish, shifting the distribution of species and even causing the accumulation of toxins up the food chain. These toxins could eventually reach the very top of the food chain, where they could pose health risks not just to wildlife, but potentially to humans as well, should they ever come into contact with Venus's environment in the future. In the face of all these toxic clouds and extreme conditions, the cascading effects on Venus's ecosystems would be devastating. The delicate balance of life that exists on Earth is, in this scenario, threatened on every level. Loss of biodiversity, the collapse of food webs, and the alteration of ecosystems are all real consequences of the presence of such toxic clouds. The understanding of these ecological impacts is crucial, especially if we are to ever consider the potential for life on other planets. It's a reminder of how fragile life can be in extreme environments and underscores the importance of studying these phenomena as we work to understand the broader dynamics of planetary ecosystems. When it comes to exploring a planet with such a corrosive atmosphere, the technological challenges are immense. Instruments and spacecraft designed for these missions must be meticulously engineered to withstand conditions that would destroy most materials in a matter of days or even hours. Engineers focus on using metals with high resistance to corrosion alongside specialized coatings that can protect against the reactive gases and particles found in the Venusian atmosphere. To ensure the spacecraft can endure the harsh conditions, extensive testing is done on the materials that will be exposed to Venus's atmosphere. Scientists simulate the extreme temperature variations and humidity levels that spacecraft will experience, pushing prototypes to their limits in accelerated aging tests. This helps identify potential weaknesses in materials and design before actual missions are launched. Protective barriers, much like a jacket shielding us from the cold, are also a critical part of the spacecraft design. Instruments can be housed within specially designed compartments that minimize their exposure to the external atmosphere, limiting damage from corrosive elements. These compartments might even feature filters to capture and neutralize harmful particles before they reach the sensitive electronics within. In the end, exploring Venus is not just about understanding the planet's atmosphere or its surface conditions. It is also about overcoming the technical challenges of surviving in one of the most extreme environments known to humankind. As we continue to study Venus and other planets with similarly hostile atmospheres, the lessons learned from these missions may one day help us better protect our own planet and the fragile ecosystems that depend on it. Monitoring systems aboard spacecraft are designed to detect a wide range of potential issues in real time, including corrosion-related problems that can compromise the functionality of essential components. These systems provide mission control with critical data, enabling them to make informed decisions on necessary adjustments or repairs. The ability to detect such issues as they arise is vital for ensuring the safety and efficiency of long-term missions. With each passing day in space, technology is continuously exposed to conditions that can cause wear and tear. And this proactive monitoring helps mitigate risks, ensuring that every part of the spacecraft is ready to face the challenges posed by the extreme and ever-changing conditions of space and the planets explored. In the case of Venus, these challenges are particularly severe. The sulfuric acid clouds that envelop the planet create an environment that is both visually and physically difficult to navigate. Imagine standing in a dense fog where visibility is nearly zero, and you are unable to discern what lies ahead. This is akin to what scientists encounter when they attempt to observe Venus. The thick, swirling clouds act like a vast veil, blocking any direct view of the planet's surface. They reflect sunlight in such a way that the surface is hidden from sight, resulting in an eerie yellowish glow that saturates the planet. This scattering effect makes it almost impossible to discern surface details with traditional visual observations, such as those conducted with telescopes. In response to these limitations, scientists have turned to more advanced technologies such as radar and infrared imaging to explore the planet. Radar waves can penetrate these dense cloud layers, bouncing off the terrain below to reveal mountains, valleys, and other geological features that would otherwise remain hidden from view. These technologies allow scientists to create detailed maps of Venus' surface, offering valuable insights into its topography and geological composition. Radar can even reveal the structure of the surface, helping scientists identify landforms and other features that give clues to the planet's geological history. The challenges of Venus extend far beyond visibility. The sulfuric acid clouds also contribute to extreme conditions on the planet's surface. High atmospheric pressure coupled with intense heat creates an oppressive environment that makes it incredibly difficult for spacecraft and landers to operate. Venus's surface pressure is about 90 times that of Earth's, and temperatures can reach a scorching 900 degrees Fahrenheit, 475 degrees Celsius. Any equipment sent to the surface must be robust enough to withstand not only the acidic clouds, but also the crushing pressure and extreme temperatures that characterize Venus's hostile environment. The presence of sulfuric acid further complicates matters, as it can corrode and damage materials over time. Yet these challenges have not deterred scientists from pushing the boundaries of exploration. In fact, they have spurred the development of cutting-edge technologies designed to withstand Venus's brutal conditions. Engineers have worked tirelessly to create spacecraft and landers that can survive the corrosive acid, high temperatures, and immense pressure, allowing for direct exploration of the planet. This drive for innovation is what has led to a series of successful missions that continue to expand our understanding of Venus and its mysteries. The sulfuric acid clouds that cover Venus also have significant implications for the planet's geology. The continuous bombardment of acid rain can dramatically alter the composition of the minerals found on the surface. Over time, sulfuric acid reacts with the minerals in the rocks, breaking down silicates and carbonates and transforming them into different compounds. The chemical reactions that occur between sulfuric acid and the minerals can lead to the formation of sulfate minerals, which have distinct chemical signatures. In addition, certain minerals that are stable on Earth may not form under Venus' acidic conditions, while other minerals, such as sulfides and sulfates, may become more prevalent. This ongoing process of chemical alteration, driven by the sulfuric acid, creates a dynamic and constantly changing surface on Venus. The constant interaction between the atmosphere and the surface means that Venus' landscape is in a state of flux, with new minerals forming, while others are dissolved away. Over extensive periods of time, this acid-rich environment could lead to the development of unique landforms and geological features that are unlike anything found on Earth. These changes provide valuable insights into the planet's geological activity and the processes that shape its surface. Moreover, the presence of sulfuric acid in Venus's atmosphere offers important clues about the planet's geological history. Sulfuric acid is often formed as a byproduct of volcanic eruptions. When sulfur dioxide, a common gas emitted by volcanoes, reacts with water vapor in the atmosphere, it forms sulfuric acid. This indicates that Venus has likely experienced significant volcanic activity in the past and may still be actively venting gases into its atmosphere. Such volcanic activity would have contributed to the thick cloud cover that surrounds the planet, as well as the extreme conditions on its surface. These ongoing geological processes suggest that Venus's surface is continually being reshaped by both volcanic and weather systems. The erosion caused by acid rain, combined with the effects of volcanic activity, means that the landscape is in a state of constant change. In this sense, the sulfuric acid clouds not only obscure the surface, but also provide a fascinating lens through which to study the planet's dynamic geology. They are a testament to the harsh conditions of Venus, which, despite their severity, offer scientists a unique opportunity to study the forces at work on a planetary scale. Through these observations, researchers are gaining a deeper understanding of the forces that shape planets, including the potential for similar processes on other worlds in our solar system. Furthermore, if tectonic activity is present on a planetary body, it may be directly linked to the movement of the planet's crustal plates, a process that facilitates the release of sulfur compounds from the planet's interior. This release plays a significant role in shaping the atmosphere, especially when sulfuric acid is involved, as it becomes a strong indicator of a planet's dynamic geological environment. Sulfuric acid doesn't just signify chemical reactions. It tells a story, one of intense volcanic eruptions and the ongoing, sometimes violent interplay between the interior and atmosphere of the planet. This constant interaction reveals a complex and evolving planetary ecosystem where the internal forces of the planet meet the external pressures from space. Such acidic environments, like those found on Venus, stand as extreme examples of hostile atmospheres in our solar system. Imagine standing on a planet where clouds of sulfuric acid rain down upon you, creating a thick, oppressive atmosphere that traps heat. The temperature is so high, the pressure so intense, it would feel like an unforgiving furnace. This stark contrast against other toxic environments across our universe is striking. For instance, while the atmosphere of Jupiter is largely composed of hydrogen and helium, it also contains dangerous substances like ammonia and methane, compounds known to be fatal to life as we understand it. On Jupiter, the intense atmospheric pressure combined with the chaotic swirling of violent storms makes the planet not only toxic, but also profoundly inhospitable. Meanwhile, on Titan, Saturn's largest moon, the atmosphere is dominated by methane and ethane, gases that exist in liquid form, creating sprawling lakes on the surface. These liquid methane lakes create a strange alien landscape where, despite the presence of organic materials, life as we know it would struggle to survive. The surface conditions are so cold, nearly 290 degrees Fahrenheit below freezing, that even traditional carbon-based life forms would find it impossible to thrive. The environment is less like a familiar world and more like a distant, cold dream of a planet. When comparing these hostile environments, Venus stands out, largely due to its combination of extreme temperatures and corrosive chemical compounds. The thick sulfuric clouds and suffocating atmospheric pressure create one of the most brutal, uninhabitable environments in our solar system. Yet, Venus is not the only place where harsh conditions reign. Each celestial body, whether it be a distant gas giant, a frozen moon, or a rocky exoplanet, presents a different form of hostility that challenges our very conception of what makes a planet inhabitable. These environments showcase the extraordinary variety of conditions that exist across the universe, stretching our imaginations and forcing us to reconsider how life might arise and persist in such extremes. The concept of terraforming, or the alteration of a planet's environment to make it more Earth-like, has long captivated the human imagination. The idea that we could reshape a world, transforming its inhospitable conditions into something more hospitable, presents both scientific challenges and opportunities. Take Mars, for example, a cold, dry, and arid world. Scientists have proposed various methods to make Mars more habitable, such as releasing certain gases into its thin atmosphere to thicken it and warm the surface. By introducing greenhouse gases like carbon dioxide, it is possible that we could trap more heat, potentially creating conditions that would allow liquid water to exist on its surface. In addition to atmospheric manipulation, another approach involves enhancing the planet's surface with life forms capable of thriving in extreme conditions. The introduction of engineered bacteria or algae could jumpstart a new ecological cycle. slowly transforming the atmosphere over time. These organisms, through the process of photosynthesis, could convert carbon dioxide into oxygen, gradually reshaping the planet's atmosphere into one that contains breathable air. This synergy between biological processes and environmental conditions would be key to the success of such an endeavor, requiring careful planning and consideration. On a broader scale, altering a planet's atmosphere could involve more dramatic technological interventions, such as space mirrors that reflect sunlight to increase the planet's temperature, or massive orbital satellites capable of regulating solar radiation. These concepts are still theoretical, but demonstrate the breadth of possibilities available for planetary engineering. However, such methods carry significant ethical, environmental, and unforeseen risks. The unpredictability of altering an entire planetary system means we must tread carefully, considering both the potential benefits and unintended consequences of such actions. Terraforming not only challenges our scientific abilities, but also forces us to confront questions about our responsibility as stewards of other worlds. While much of this remains in the realm of theoretical exploration, the pursuit of terraforming reflects humanity's deep-seated desire to expand our horizons and ensure our survival in the vastness of the cosmos. The idea of transforming distant, lifeless planets into homes for future generations embodies the quest to extend the boundaries of life itself, offering the possibility of new beginnings beyond our own planet. The discovery of hostile environments on other planets has led to profound shifts in how we think about habitability. For a long time, scientists and thinkers believed that for a planet to support life, it needed to have Earth-like conditions: mild temperatures, liquid water, and a breathable atmosphere. However, as our exploration of exoplanets, planets located outside of our solar system, advances, it is becoming clear that many of these worlds harbor extreme conditions that would seem inhospitable, even impossible, for life as we know it. Take, for example, the so-called hot Jupiter category of exoplanets. These massive gas-rich worlds orbit extremely close to their stars, producing surface temperatures so high that they could melt metals. Such conditions are far too intense to support life as we currently understand it. However, despite these extreme environments, scientists are beginning to consider alternative forms of life that could potentially emerge on such worlds. This pushes the boundaries of what we once thought was possible and forces us to reconsider our long-held belief that life can only thrive in familiar Earth-like habitats. Similarly, the moons of Jupiter and Saturn, such as Europa and Enceladus, have become focal points of exploration. These moons are characterized by frigid conditions with icy surfaces that hide vast oceans beneath. The potential presence of liquid water warmed by geological activity beneath the ice opens up the possibility of life existing in complete darkness, far removed from the warmth of the sun. This realization challenges traditional definitions of habitability, pushing scientists to rethink what conditions might allow life to survive. The exploration of such environments also deepens our understanding of the incredible resilience and adaptability of life. If life can exist in the frigid depths of Europa's ocean or in the toxic clouds of Venus, then perhaps life could emerge in ways we have yet to imagine. This evolution in perspective shifts our search for extraterrestrial life, broadening the criteria we use to define what makes a world habitable. In addition to these extremes, other planets present fascinating puzzles for astrobiologists. Take Mercury, for example. This planet is often described as tidally locked, meaning that one side of the planet constantly faces the sun while the other side remains in perpetual darkness. However, Mercury's relationship with the sun is far more complex than that of a typical tidally locked world. Mercury rotates 3 times on its axis for every 2 orbits it completes around the sun, creating a unique dynamic between its day and night cycle. This results in stark environmental differences across the planet's surface. The side of Mercury facing the sun experiences extreme temperatures, soaring to unbearable highs during the long day as the solar rays bathe the surface relentlessly. These inhospitable conditions, coupled with the extreme cold on the dark side of the planet, make Mercury a world of contrasts, one that seems far removed from the conditions necessary to support life. In exploring these varied and extreme environments, we come to realize that life could potentially exist in forms and places we have never before imagined. The universe offers an incredible diversity of conditions, and in each, the potential for life, or at least for some form of complex chemistry, exists in ways we are only beginning to understand. As we push the boundaries of our exploration and understanding, we are forced to expand the very definition of what it means to live in the universe. Conversely, the night side of a planet can experience freezing cold, largely because it is deprived of sunlight for extended periods of time. These long stretches of darkness lead to temperature extremes that can create a lack of atmosphere capable of sustaining weather systems, ultimately producing a surface that is barren, desolate, and scarred by craters. These craters have accumulated over billions of years due to countless impacts, leaving behind a surface that is as much a record of the planet's tumultuous past as it is a reflection of the extreme conditions that still persist today. The rotational dynamics of such a planet also play a critical role in shaping its environment. The slow transition between day and night causes each hemisphere to remain in one state, either in light or darkness, for long periods, leading to environments that are drastically different from those on planets with more balanced day-night cycles. On these more typical planets, climates can support a variety of atmospheric and weather phenomena, ranging from rainfall to seasonal changes, creating the possibility for more diverse ecosystems. In stark contrast, the planet with a slow rotation or tidal locking, where one hemisphere is always facing the star, experiences a very different reality. On planets that are tidally locked, the side facing the star is subjected to continuous daylight. This unrelenting exposure to sunlight causes temperatures to soar to extreme heights, creating a hot, desert-like environment. In such conditions, any existing water sources will rapidly evaporate, leaving behind a dry, inhospitable atmosphere. If life were to exist in these conditions, it would need to have highly specialized adaptations to cope with the heat and lack of moisture. These life forms might develop reflective surfaces to minimize heat absorption or mechanisms to store and conserve water, crucial to their survival. On the opposite side of the planet, where there is perpetual darkness, the environment is entirely different. The absence of sunlight leads to an environment marked by frigid temperatures. In this cold, frozen landscape, ice and snow dominate, and the lack of warmth means that any remaining water sources are likely to be locked in solid form. The extreme chill creates a barren, inhospitable environment where life, as we know it, would struggle to survive without radical adaptations. Water, essential for most known life forms, would be frozen, and the landscape itself would be defined by ice and snow. However, the transition zone between the night and day sides of the planet, often referred to as the terminator, presents a fascinating region. Here, the blending of the hot and cold environments creates unique dynamics. The temperature gradients between the two sides can result in dramatic shifts in climate, leading to the formation of unusual weather patterns. As warm air from the sunlit side meets the cold air from the dark side, powerful winds and atmospheric turbulence can develop. This meeting of hot and cold air masses can generate storms and precipitation, which may give rise to dynamic, fluctuating weather systems. In this region, life forms may find a delicate balance between the extremes, developing the ability to cope with fluctuating environmental conditions, making it one of the most diverse and resilient zones on the planet. These contrasting climates between the scorched, sunlit side and the frozen, dark side offer a compelling example of how life might adapt in radically different environments. Studying such extremes opens up new possibilities for what life might look like on alien worlds, helping scientists understand the potential resilience and adaptability of life in environments vastly different from those found on Earth. Extreme temperature differentials on a planet can have profound effects not only on its surface, but also on its atmosphere. Picture a scenario where one hemisphere of a planet is constantly bathed in sunlight, while the other side remains in unending darkness. The intense heat on the sunlit side would create scorching surface temperatures, causing materials to crack and erode. Water would evaporate, leaving behind a dry, barren landscape. Soils would dry out, and the surface would become increasingly inhospitable to life. In contrast, the dark side of the planet would present an equally harsh but fundamentally different environment. The lack of sunlight leads to frigid temperatures, potentially allowing ice and snow to dominate the landscape. The absence of warmth means that any remaining water would freeze, making the environment even more hostile. Life, as we understand it, would face a near impossible task in surviving such conditions. The interaction between the extreme hot and cold regions influences the planet's atmosphere in significant ways. Warm air rises from the sunlit side, creating areas of lower pressure, which in turn leads to turbulent winds as cooler air rushes in to fill the gaps. These winds can drive weather systems, generating storms as air masses from the heated and frozen zones collide. Over time, this dynamic exchange between hot and cold air masses can lead to the formation of thick cloud layers, which, under certain conditions, could result in precipitation and violent weather patterns. These extreme variations in temperature and pressure cause continuous atmospheric shifts, making the planet's environment ever-changing and unpredictable. The surface features of such a planet would be continually shaped by the interactions between these extreme weather systems. Powerful winds and dust storms can erode the landscape, carving out new features or further shaping existing ones. Thermal expansion and contraction, caused by the drastic temperature swings, could cause cracks and breakages in the surface materials, further altering the planet's topography. These constant shifts, marked by the battle between heat and cold, ensure that the planet remains a dynamic, ever-changing world. Scientists have long been fascinated by the resilience of life, particularly in extreme environments. On Earth, extremophiles, organisms that thrive in conditions that would be hostile to most life forms, offer a glimpse into how life might adapt to even harsher conditions. For example, certain bacteria live in hot springs where temperatures can reach boiling points, their specialized proteins remaining stable and functional despite the intense heat. If life exists on planets with similar extreme conditions, it is likely that such organisms would have developed unique adaptations to cope with the challenges of their environment. In other extreme environments, life forms might evolve features like thicker outer membranes to protect against radiation, or develop specialized biochemical pathways to metabolize substances that would be toxic to most organisms. In these alien worlds, the organisms that thrive may bear little resemblance to anything on Earth, yet their ability to adapt to their environments would showcase the incredible versatility of life itself. In conclusion, the extreme conditions faced by planets with slow rotations or tidal locking offer a fascinating opportunity to explore how planetary features, like temperature variations and the interaction between sunlight and darkness, shape environments and influence the potential for life. These extreme contrasts between light and dark, heat and cold, create environments that are both inhospitable and yet brimming with potential for life forms adapted to those very conditions. The study of such worlds not only deepens our understanding of what life might look like beyond Earth, but it also highlights the power of adaptation and resilience in the face of extreme challenges. The ability of life forms to survive in extreme conditions is a fascinating topic, one that hinges on their capacity to adapt and endure. Survival might not always depend on the immediate availability of food, water, or oxygen, but rather on the ability of organisms to enter a dormant state, allowing them to withstand unbearable conditions until the environment becomes more suitable. This phenomenon is not merely theoretical. On Earth, certain microbes have demonstrated an incredible ability to remain viable for years, even in a desiccated state. They wait for moisture to return, and once conditions become favorable, they spring back to life. This concept of dormancy, a survival mechanism, could also be a potential strategy for life forms existing on other planets. Imagine a planet with harsh and unpredictable environments where extreme temperatures, radiation, or lack of resources make life untenable for long periods. Under such conditions, life forms may not only endure, but evolve. Through natural selection and genetic mutations, organisms could develop the ability to withstand such environments, perhaps by utilizing available resources in novel ways or forming symbiotic relationships with other life forms. Over long periods, these adaptations could become increasingly specialized, allowing these organisms to survive in ways we cannot yet fully predict. In such extreme environments, survival might not be the rare exception, but the norm. Nature's ingenuity would be on full display as organisms evolve traits that seem almost miraculous. Whether through the ability to draw energy from unexpected sources or by forming complex partnerships with other life forms, the possibilities for how life could adapt are vast and varied. This scenario underscores just how resilient and resourceful life can be, adapting to environments that might appear inhospitable to us at first glance. A particularly intriguing case to explore in this context is that of tidally locked planets, those where one side perpetually faces their star while the other remains in constant darkness. The gravitational interaction between a planet and its star profoundly influences its geological features. The result is an intriguing juxtaposition of extremes. One side of the planet is constantly bathed in light and warmth, while the other is cloaked in darkness and cold. This extreme disparity creates distinct, almost polarized geological conditions. On the sunlit side, temperatures can soar to unbearable highs, fostering intense geological activity. Imagine vast barren plains, punctuated by the remnants of ancient volcanic eruptions. The land would be marked by old lava flows, which serve as evidence of a history written in fire. Over time, this warmth could give rise to sprawling deserts, where the wind itself carves out extraordinary rock formations, towering mesas or intricate canyons, shaped by the relentless forces of erosion. The process of weathering would be accelerated here, breaking down rocks into fine dust or sand that sweeps across the surface in swirling gusts. It is a landscape of extremes, where the very ground seems to bear witness to the unyielding forces of nature. In stark contrast, the dark side of the planet presents an entirely different world. Here, temperatures plunge to frigid extremes, and any water that exists would be frozen solid. The surface would be marked by icy plains and glaciers, and the frozen terrain could resemble the deep polar regions of Earth, where life struggles to survive. The absence of sunlight would make this side geologically inactive, with little erosion from wind or water. Instead, the landscape would likely be pocked with ancient impact craters, their rims sharply defined against the unyielding cold. Over millennia, this side of the planet would become a frozen, silent world, eerily still in its desolation. Yet, the most fascinating area would likely be the terminator, the boundary line between light and dark. In this zone, the temperature differences are so extreme that they could create dynamic, ever-changing geological features. The transition zone, as it's known, is where the two worlds meet, creating an environment ripe for geological processes like weathering and sedimentation. Imagine sharp mountain peaks jutting upward into the warm sunlight, while deep valleys below remain perpetually cloaked in shadow and ice. The interplay of heat and cold would sculpt the landscape in unpredictable ways, creating a series of jagged, ever-shifting features. This boundary area is not merely a static line, but a dynamic space where the very forces of nature converge and clash. The processes that govern the climate on a tidally locked world are equally fascinating. The stark temperature differences between the sunlit and dark sides create a constant flow of air. As warm air rises on the sunlit side, it creates an upward movement that lowers pressure in the atmosphere. In contrast, the dense, cold air on the dark side sinks, creating a powerful circulation of air between the two zones. This atmospheric movement can create powerful winds that vary in intensity, depending on the size of the temperature differential between the two sides. The greater the disparity, the faster and more vigorous the winds become. These winds could reach speeds so high that they form intense storms, particularly at the terminator, where the clash of warm and cold air creates volatile weather conditions. The interactions between heat, wind, and moisture would further shape the weather patterns on such a planet. For instance, if liquid bodies of water, oceans, lakes, or rivers exist, they would play a crucial role in distributing warmth from the sunlit side to the dark side. While the dark side remains cooler than the sunlit side, these currents could gradually warm it over time, creating a delicate balance between extremes. Despite this, the dark side would always remain colder, but the sheer complexity of the climate dynamics on a tidally locked planet makes it a fascinating study. The terminator line itself, where light and dark meet, is not just a boundary, but a critical zone for understanding planetary climates. On Earth, this line can be observed during sunrise and sunset, but on other planets, it plays a much more significant role in shaping climate systems. The transition zone between light and dark creates dramatic temperature gradients which in turn influences the movement of air. Warm air rises while cold air sinks, creating a circulation pattern that can lead to dynamic weather systems. The study of this line is crucial for understanding how a planet's atmosphere behaves. For example, on Mars, where the thin atmosphere leads to extreme temperature fluctuations, the terminator line marks the edge between day and night, impacting everything from dust storms to frost formation. On gas giants like Jupiter, the terminator line has an even more profound impact. Since sunlight only penetrates halfway through the dense atmosphere, the resulting temperature differences between the illuminated and dark sides create distinct weather systems. Understanding how these zones interact provides scientists with valuable insights into the planet's overall climate dynamics. By studying temperature fluctuations, atmospheric pressures, and wind patterns near the terminator, researchers can develop more accurate models of energy distribution on planetary scales, providing clues about climate behavior elsewhere in the universe. For future exploration or colonization missions to tidally locked planets, these extreme environmental differences pose significant challenges. The sunlit side may be too hot, with intense solar radiation making it inhospitable without sophisticated technology to shield habitats. On the other hand, the dark side could be freezing, with temperatures so low that any water present would turn to ice. These extreme conditions would require innovative solutions for colonization, demanding technology that can handle such extremes. Teams would need to develop habitats capable of withstanding these harsh environments, ensuring the survival of any explorers or settlers brave enough to venture into this extreme world. In conclusion, tidally locked planets, with their dynamic and contrasting environments, offer a unique perspective on the resilience of life and the adaptability of nature. Whether through dormant states that enable survival or complex geological and atmospheric systems that shape the planet's surface, such worlds provide a window into the possibilities of life beyond Earth. The challenges they present are daunting, but the ingenuity of nature, whether on Earth or in distant corners of the universe, remains a source of endless wonder and exploration. Tidal locking is a celestial phenomenon that profoundly influences the behavior of planets and moons throughout the cosmos. It occurs when a celestial body's rotation period becomes synchronized with its orbit around another body, meaning one side of the planet or moon always faces its parent, while the other side is perpetually hidden in shadow. This unique characteristic reshapes the very nature of life, energy, exploration, and settlement on such worlds. On a planet exhibiting tidal locking, the constant sunlight on one hemisphere and unbroken darkness on the other could significantly impact the planet's energy systems. The sunlit side would become a thriving hub for solar energy generation, fueling the planet's various activities and sustaining the maintenance of habitats. Solar panels would soak in the relentless sunlight, producing an abundance of energy that could sustain a wide array of technological systems, from life support to industrial operations. However, the dark side poses its own set of challenges. With no natural light to harness, alternative energy solutions would be crucial. The absence of sunlight would necessitate the use of other forms of power, such as nuclear or geothermal energy. If the planet exhibits geological activity, geothermal sources could be tapped, providing a stable and reliable energy supply. On the other hand, nuclear energy might become the go-to solution for energy-hungry systems, ensuring the survival of colonies in this seemingly inhospitable environment. Exploration itself would be deeply affected by the phenomenon of tidal locking. Missions to such a planet would need to carefully consider the extended cycles of day and night, which could last for weeks or even months, depending on the planet's orbital period. With the rotating hemisphere receiving constant sunlight and the other in perpetual darkness, mission planners would have to design strategies that account for these extreme conditions. The twilight regions, where the transition between light and dark occurs, could emerge as prime locations for exploration and colonization. These areas might offer a more temperate climate, presenting a balance between the searing heat of the sunlit side and the frigid cold of the dark side, making them more conducive to long-term settlement. Tidal locking is not just a theoretical curiosity, it is a reality for several moons and planets within our own solar system. The most famous example is Earth's own moon, which is tidally locked to our planet, always showing the same face to us. This phenomenon, though well known, also occurs in other parts of the solar system, with Pluto's relationship with its largest moon, Charon, being a striking example. Pluto and Charon share a unique gravitational bond with their common center of mass located outside of either body, resulting in an intriguing gravitational dance as they orbit one another. This configuration is not just a quirky oddity, but an essential part of their orbital mechanics. Another striking case of tidal locking is found among the moons of the gas giants like Jupiter and Saturn. For example, many of Jupiter's moons, such as Io, Europa, and Ganymede, are tidally locked to the planet, meaning that the same side of each moon constantly faces Jupiter. This creates a fascinating contrast. One hemisphere of each moon experiences constant daylight, while the other remains in eternal darkness. A similar situation exists with Saturn's moon Titan, which, like its Jovian counterparts, is tidally locked to the gas giant. Titan's unique relationship with Saturn is a testament to the immense gravitational pull the gas giants exert on their moons. The influence of the primary body's size and mass plays a crucial role in the dynamics of tidal locking. Smaller moons, such as those orbiting Jupiter, can achieve tidal locking relatively quickly due to their proximity to their parent planet. In contrast, larger bodies like Pluto and Charon evolve more slowly toward tidal equilibrium because of their greater distance from each other and the smaller mass of their primary. This gradual process, unfolding over millions of years, reflects the intricate gravitational interactions at play in these systems. By examining these various examples, scientists can gain deeper insights into the evolutionary history of planetary systems. Tidal locking serves as a reminder of the interconnectedness of the universe, where gravitational forces govern the physical characteristics of celestial bodies. These gravitational interactions shape the landscapes and atmospheres of moons and planets, offering clues about the forces that drive the formation and evolution of solar systems. Tidal locking also provides a lens through which we can better understand atmospheric dynamics. On tidally locked moons, the stark contrast between the eternal day and night creates complex weather patterns. The sunlit side, with its constant heating, can experience extreme temperature fluctuations, driving the formation of winds, storms, and other atmospheric phenomena. Meanwhile, the dark side remains cold and stable, offering little to no atmospheric movement. This extreme variation between the two hemispheres might mimic the kinds of conditions found on exoplanets orbiting distant stars. By studying these phenomena in our own solar system, we can better predict how atmospheres might behave on planets outside our solar system that experience similar tidal locking effects. As we continue to explore the outer reaches of our solar system and beyond, the study of tidal locking will provide valuable insights into the dynamics of celestial bodies. From energy generation to exploration, the influence of this phenomenon will shape how we approach colonization, settlement, and survival on distant worlds. Understanding the subtleties of tidal locking and how it affects the environment and atmosphere of celestial bodies is essential for developing strategies that will ensure the safety, sustainability, and success of missions to these fascinating and often extreme worlds. In the vast expanse of the cosmos, the intricate gravitational interactions between celestial bodies reveal a fascinating phenomenon that shapes the very nature of planetary systems. When one body exerts a dominant gravitational influence over another, it gives rise to tidal forces, which can significantly alter the rotational and orbital behaviors of nearby objects. These forces, often subtle yet profound, provide crucial insights into the dynamics that govern how planets, moons, and stars interact. The concept of tidal locking in particular is an intriguing example of how these interactions unfold. Tidal locking occurs when a celestial body's rotation becomes synchronized with its orbit around another body. This process results in one hemisphere of the body always facing its parent, while the other side remains perpetually dark. Such a phenomenon offers more than just a fascinating astronomical observation. It also has profound implications for the potential habitability of planets and moons. When examining planets locked in this manner, we begin to see the delicate balance between extreme environmental conditions. The side facing the star, or the sunlit side, could experience stable and moderate temperatures due to a lack of rotation, while the opposite side, bathed in perpetual darkness, might have significantly cooler conditions. These temperature variations could create ecosystems that differ drastically from those on Earth. As a result, tidal locking opens up an entirely new framework for identifying potentially habitable exoplanets. It suggests that even in systems where conditions might seem inhospitable, life could find a way to thrive, especially if the planet has developed mechanisms to balance the extremes between day and night. This nuanced understanding of how gravitational forces shape planetary characteristics invites new questions about the potential for life beyond our solar system. What might life look like on a tidally locked world? Could stable climates on the sunlit side support complex ecosystems, while the dark side remains a mysterious, frozen wasteland? These questions expand the criteria used by astronomers and astrobiologists as they search for signs of life on distant exoplanets, offering us a richer perspective on what it means for a planet to be habitable. As we delve further into the gravitational dynamics of celestial bodies, another type of extreme environment emerges: the supervolcanic planet. These worlds stand out due to their extraordinary volcanic activity, capable of reshaping entire landscapes and influencing atmospheric conditions on a monumental scale. Unlike the volcanic systems we're familiar with here on Earth, supervolcanoes on these planets erupt with a power and frequency that far surpasses typical volcanic activity. They are characterized not only by their size, but also by the sheer volume of magma and volcanic material they release. These eruptions can be thousands of times more powerful than those seen on Earth, leading to dramatic changes in the planet's surface and atmosphere. The origins of these supervolcanic eruptions are deeply rooted in the planet's internal dynamics. These planets tend to have vast reservoirs of molten rock beneath their surfaces, a direct result of significant geothermal heat and tectonic forces. The heat within these planets can come from a variety of sources, such as the cooling of the planet's core or the decay of radioactive elements. As the molten rock builds up, it exerts immense pressure on the planet's crust. When the pressure becomes too great, it forces its way to the surface through cracks and fissures, triggering explosive volcanic eruptions. This cycle of pressure accumulation and subsequent release creates a rhythmic, almost relentless pattern of volcanic activity. The eruptions themselves are not only spectacular displays of raw energy, they also significantly impact the planet's geological and atmospheric features. Supervolcanic planets often possess massive calderas, huge depressions formed after explosive eruptions that can collect erupted material and provide the conditions for subsequent volcanic activity. These features can reshape the landscape, forming vast plains or towering mountains, and contribute to the ongoing volatility of the planet. In addition to their geological significance, supervolcanoes can also alter the atmosphere on a global scale. The gases released during an eruption, such as carbon dioxide, sulfur dioxide, and water vapor, can influence the climate by creating thick clouds that block sunlight, leading to cooling effects. Over time, the ash and sulfur particles released into the atmosphere can create a persistent haze that reflects sunlight, subtly lowering global temperatures. These atmospheric changes can affect weather patterns and even disrupt ecosystems by reducing the amount of sunlight reaching the surface, which in turn impacts photosynthesis and the overall food chain. Yet, despite the inhospitable nature of supervolcanic planets, they offer a unique perspective on planetary evolution. Their volatile nature, driven by internal heat and tectonic activity, reminds us that planets are dynamic systems that undergo constant transformation. The continual reshaping of landscapes and atmospheric composition on such planets serves as a powerful reminder of the forces at play within our universe. In the case of Earth, we are familiar with the dramatic effects of volcanic eruptions. Lava flows can create new landforms, such as islands or mountains, while ash fallout can blanket vast areas, burying forests or farmlands. Over the long term, however, volcanic activity has a more subtle influence on the environment. The minerals in volcanic ash and lava enrich the soil, enhancing agricultural productivity and contributing to the fertility of the land. But this positive impact often comes at a significant cost, especially in the short term, when volcanic eruptions can lead to widespread destruction, loss of life, and long-lasting disruptions to local climates. These massive eruptions have the potential to drastically alter the landscape of supervolcanic planets in a similar way, but on an even larger scale. In these extreme environments, volcanic activity plays a central role in shaping the planet's geological features, atmosphere, and even its potential to support life. The eruption of supervolcanoes might not only carve out new features on the planet's surface, but could also create conditions that challenge or even extinguish life. And yet the very same volcanic processes might give rise to entirely new forms of life, adapted to the harsh and ever-changing environment. By studying the extremes of tidal locking and supervolcanism, we gain valuable insights into the diversity and complexity of planetary systems. We come to understand that the universe, far from being a static or unchanging place, is full of dynamic forces that continually shape the worlds within it. From the tidal forces that lock moons in eternal synchrony with their parent planets, to the violent eruptions of supervolcanic planets, each celestial body tells a unique story. These stories not only deepen our understanding of how planets and moons coexist, but also broaden our search for life beyond Earth. In doing so, they enrich our understanding of our cosmic neighborhood and the many factors that contribute to the creation and destruction of worlds. Volcanic activity, with its constant presence on Earth, plays a pivotal role in shaping the planet's surface. Over time, these eruptions contribute to the creation of new geological features such as calderas and volcanic craters, further emphasizing the dynamic and ever-changing nature of our world. Every eruption serves as a stark reminder of the immense power hidden deep within Earth, a force that drives both destruction and renewal, continuously transforming the landscape. The delicate balance between these two forces highlights the planet's ongoing evolution, constantly reshaping its physical form and geology. Volcanic eruptions, however, are not all the same. They vary greatly in terms of type, intensity, and impact. This variation is influenced by a multitude of factors, such as the composition of the magma, the geological setting of the volcano, and the underlying physical processes occurring beneath the surface. There are several well-known eruption styles that are observed across the globe, each with its unique characteristics and consequences for the environment. One of the most common eruption styles is the effusive eruption, where lava flows gently from the volcano, often in a continuous stream. These eruptions occur when the magma is relatively low in viscosity, making it easy for it to flow out of the volcano. Hawaiian volcanoes, for instance, are prime examples of effusive eruptions. The lava flows from these volcanoes can last for days, months, or even years, creating long-lasting, river-like lava streams that gradually reshape the surrounding landscape. Although effusive eruptions are less violent compared to others, they still present significant hazards, particularly if they occur in populated areas. However, they generally cause fewer immediate dangers when compared to explosive eruptions. In contrast to effusive eruptions, explosive eruptions are characterized by sudden, violent bursts of energy. These eruptions typically occur when magma is thick and gas-rich, preventing the gases from escaping easily. The buildup of pressure becomes so immense that it eventually results in an explosive release of energy. Mount St. Helens in the United States is perhaps one of the most well-known examples of explosive eruptions. Its 1980 eruption was marked by an enormous explosion that sent ash clouds into the atmosphere, while pyroclastic flows devastated the surrounding landscape. Explosive eruptions can cause widespread destruction as the pressure forces magma, ash, and gases into the atmosphere, with far-reaching consequences for both the environment and human populations. Then there are intermediate eruption types such as strombolian eruptions. These eruptions produce bursts of lava and gas that are forcefully ejected into the atmosphere. While they are less destructive than explosive eruptions, strombolian eruptions still pose significant hazards. Stromboli, an active volcano off the coast of Italy, regularly exhibits this eruption style, with frequent rhythmic bursts of lava. These eruptions are not as dramatic as explosive eruptions, but still create stunning visual displays, with lava fountains reaching great heights before falling back to the volcano's surface. The intensity of volcanic eruptions is often categorized using a scale that takes into account a variety of parameters, such as the volume of eruptive material, the height of the eruption column, and the duration of the eruption. A particularly explosive eruption, for instance, might yield vast quantities of ash, spreading it over hundreds or even thousands of kilometers. On the other hand, effusive eruptions are generally more gradual and contribute to the formation of new land masses over time. Geographically, volcanic activity is most commonly found along tectonic plate boundaries, although some volcanoes are located over hotspots where magma rises from deep within the Earth's mantle. Subduction zones, where one tectonic plate is forced beneath another, often produce explosive eruptions. The accumulation of thick, viscous magma creates pressure that eventually leads to violent eruptions. Conversely, mid-ocean ridges and hotspots tend to generate more effusive eruptions, where the magma flows more freely, creating shield volcanoes and gradual land formation. The variety of eruption types and intensities highlights the complex interactions between volcanic materials, the surrounding environment, and the geological processes at work. Understanding these differences is crucial not only for gaining insight into the volcanic landscape itself, but also for improving safety measures for communities living in close proximity to active volcanoes. Interestingly, volcanic activity is not limited to Earth. Other celestial bodies in our solar system, such as Mars, Venus, and some of Jupiter's moons, also display volcanic phenomena, albeit under different conditions. While Earth's volcanic activity is driven by tectonic shifts and the movement of a dynamic crust on a molten mantle, other planets and moons experience volcanic processes influenced by factors like atmospheric pressure, planet size, and heat retention. For example, Mars features massive shield volcanoes that appear to have formed due to the persistent outpouring of lava. The absence of plate tectonics on Mars suggests that its volcanic activity may be driven by different processes than those found on Earth. In addition, some of Jupiter's moons, such as Io, exhibit intense volcanic activity that is far more extreme than what we observe on Earth. This is due to tidal heating, a process driven by the gravitational pull exerted by Jupiter and other moons. Io's volcanic eruptions are not only frequent but incredibly energetic, creating an environment that is markedly different from Earth's volcanic systems. The gravity-driven mechanisms behind these eruptions produce lava flows and eruption patterns that are unique to this moon. The study of volcanic activity beyond Earth not only enhances our understanding of other celestial bodies, but also provides valuable insights into the broader dynamics of planetary formation and evolution. Volcanism on these planets and moons echoes Earth's own geological history, but the processes behind these eruptions can differ greatly. By studying volcanic activity in space, scientists gain a more comprehensive understanding of the forces that shape planets from their core to their surface. To study volcanic activity in space, scientists rely on advanced technology and remote sensing techniques. These tools allow researchers to observe and monitor volcanic regions from a safe distance, avoiding the direct dangers posed by active volcanoes. Satellite imagery is one of the most crucial instruments in this field, providing broad coverage of volcanic regions and enabling the monitoring of changes in landforms, thermal emissions, and ash dispersal patterns. By detecting heat, satellites can help determine the activity level of a volcano, as warm spots often indicate rising magma beneath the surface. Ground-based remote sensing also plays a significant role in studying volcanoes. Techniques like laser altimetry allow scientists to map the topography of volcanoes with incredible precision, revealing changes in elevation and surface deformation that may signal an impending eruption. Radar systems can penetrate cloud cover to measure ground movement and detect the release of volcanic gases, which can be key indicators of eruptive activity. Additionally, weather balloons equipped with gas sampling instruments can collect data on gases like sulfur dioxide, which is often released during volcanic eruptions. This information is vital for assessing potential risks and understanding the behavior of the volcano. Acoustic sensors are another invaluable tool in the study of volcanic eruptions. These sensors capture the sounds generated by the eruptions, helping scientists gauge their intensity and frequency. By using a combination of satellite imagery, ground-based observation, and in-field instrumentation, researchers can gain a detailed, real-time picture of volcanic behavior. This multifaceted approach allows for more accurate predictions and better informed safety measures for communities living in the shadow of active volcanoes. Finally, the volcanic landscape itself is home to some of the most fascinating and unique mineral formations on Earth. When a volcano erupts, it releases a variety of materials, including magma, gases, and ash. As the magma cools and solidifies, it can form a wide range of mineral crystals, many of which would not form in more stable environments. Volcanic activity also alters existing rock formations, leading to processes such as hydrothermal alteration. Hot fluids can permeate cracks in the rock, reacting with minerals and creating new compounds unique to the volcanic environment. This process is responsible for the formation of valuable mineral deposits, such as copper, gold, and rare earth elements, which are essential for modern technology. The chemical composition of the materials released during volcanic eruptions varies greatly depending on the type of volcano and the surrounding tectonic conditions. For example, one volcano may produce obsidian, a glassy volcanic rock, while another may create pumice, which is much lighter in weight and filled with air pockets. These differences in composition contribute to the complexity and diversity of the mineral landscape found in volcanic regions. Additionally, the extreme temperatures generated by volcanic activity facilitate the formation of minerals that would be unstable under normal Earth conditions, offering a glimpse into the unique geological processes that occur deep within our planet. Volcanic gases, such as sulfur dioxide, play a crucial role in the formation of sulfide minerals, which are often rare yet highly valued for various industrial applications. The intense volcanic environments, with their extreme conditions, harbor a unique opportunity for exploration, revealing an extraordinary array of minerals. From the vibrant hues of brightly colored crystals to the robust nature of metallic ores, these landscapes are a natural laboratory, constantly offering new insights into the Earth's geological processes. For geologists and mineralogists, every eruption is a new chapter in the unfolding story of our planet's mineralogical diversity. In many ways, volcanic regions are like treasure chests, continually redefined by each eruption, exposing valuable resources and expanding the scientific understanding of our planet's richness. Each volcanic eruption is a gateway to uncovering previously hidden secrets, making these regions an unending source of scientific inquiry. The interplay of fire and rock not only shapes the land, but also reshapes our knowledge of the Earth's inner workings, creating an environment where exploration can reveal wealth far beyond what we might imagine. The eruption of volcanoes, driven by intense internal forces, serves as a dynamic reminder of the planet's constantly changing nature, offering opportunities for discovery that could change the course of scientific understanding. Similarly, the prospect of sending a mission to a volatile planet presents an intriguing mixture of risk and reward that could fundamentally alter our comprehension of the universe. The potential gains are enormous. Each mission has the possibility of unveiling new, groundbreaking knowledge about a planet's atmosphere, geology, and even its history. Such discoveries could provide critical clues about the evolutionary processes of planets, enhancing our understanding not just of Earth, but of other celestial bodies throughout the universe. These findings could lead to advancements that enable better protection of our planet from cosmic threats, or they could provide key information for humanity's future colonization efforts elsewhere in space. However, the risks are equally monumental. Volatile planets are characterized by extreme conditions such as intense temperatures, fierce storms, and unpredictable geological activity, all of which pose significant challenges to both technology and human life. The extreme atmospheric conditions could wreak havoc on spacecraft, making data collection difficult or even rendering safe landing a near impossibility. The risks of radiation or volcanic eruptions further compound the dangers, making prolonged missions perilous. Even seemingly minor events like equipment failure or unforeseen environmental hazards could jeopardize the entire mission, resulting in the loss of valuable scientific instruments or, in the worst case, the loss of the mission itself. Despite these dangers, the potential rewards far outweigh the risks. Each mission into the unknown is a step forward in expanding our scientific horizons, pushing the boundaries of what we know about our solar system and beyond. These daring explorations not only satiate humanity's boundless curiosity, but also provide a foundation for technological advancements that could benefit us all. Ultimately, while exploring volatile planets may carry risks, the knowledge gained has the power to reshape our understanding of the cosmos and open doors to future endeavors that could impact generations to come. In order to understand why certain planets exhibit such intense volcanic activity, scientists delve deep beneath their surfaces, studying the internal structures that drive these extraordinary events. At the core of many planets, including Earth, is a dense metallic center surrounded by a layer of molten rock known as the mantle. This mantle is far from static. It is constantly active and convective. To understand how, imagine a pot of boiling water. Heat from the bottom causes the water to churn and circulate, creating currents. Similarly, the heat generated by a planet's core causes its mantle to move, producing convection currents. These currents generate immense pressure in certain regions, which can lead to the melting of materials within the mantle. When enough magma forms, it rises toward the surface, and if there's a pathway available, it escapes, resulting in volcanic eruptions. Not all planets experience volcanic activity in the same way, however. Take Venus, for example, which showcases enormous volcanic plains and massive shield volcanoes. These features suggest that Venus has been subjected to sustained geological activity over millions of years. Such endurance may be due to a thicker atmosphere and different pressure conditions, which allow magma to constantly form and make its way to the surface. This contrasts with other planets that may exhibit less frequent or less intense volcanic activity, offering scientists valuable insight into the complex and varied geological processes that shape planets across the cosmos. In conclusion, scientists hypothesize that the intense volcanic activity observed on certain planets is largely due to ongoing heat from their cores, dynamic mantle convection, and unique surface pressures that allow magma to rise freely. This activity offers a fascinating window into the inner workings of celestial bodies, shedding light on the complex geological processes that govern their evolution. Understanding these processes is crucial not only for understanding individual planets, but also for piecing together the broader narrative of planetary formation and evolution throughout the universe. The possibilities for life beyond Earth are far more expansive than we often assume. Extremophilic organisms, life forms that thrive in the most extreme conditions on Earth, provide an exciting glimpse into the potential for life in far-off alien environments. These remarkable organisms can be found in boiling hot springs, frigid ice caps, and the acidic depths of Earth's oceans. Their existence raises the tantalizing possibility that similar forms of life might be able to survive in environments resembling those of other planets or moons in our solar system. Consider Europa, one of Jupiter's moons, which has an icy crust concealing a vast ocean beneath its surface. This environment could support life similar to the extremophiles found on Earth. The ocean, warmed by tidal heating from gravitational interactions with Jupiter, could offer the necessary conditions for life to thrive. The chemical ingredients within the subsurface ocean, coupled with the warmth provided by these tidal forces, could create a fertile environment for microbial life to develop. Mars, too, presents a compelling case for the potential of life beyond Earth. While its surface is harsh, characterized by a thin atmosphere, extreme cold, and intense radiation, evidence of ancient riverbeds and minerals suggests that water once flowed on its surface. This discovery has led scientists to speculate that simpler life forms may have existed on Mars in the past, possibly in subsurface regions where conditions are more stable and protective. Similarly, Enceladus, a moon of Saturn, has plumes of water vapor erupting from its surface. Studies of these geysers reveal the presence of organic compounds, hinting at a subsurface ocean beneath. This discovery offers the tantalizing possibility that Enceladus could harbor microbial life, thriving in its watery depths, much like the organisms found around Earth's hydrothermal vents. The conditions found on these moons and planets may not be as alien as we once thought, and the adaptability of extremophiles gives scientists hope that life could exist in even the most inhospitable environments throughout the cosmos. Whether considering tidally heated worlds, subterranean lakes, or even the thick atmospheres of gas giants where microbial life might reside within the clouds, the versatility of extremophiles is a powerful reminder that life might find a way to thrive in the universe's most extreme habitats. This adaptability is one of the driving forces behind our quest to discover life beyond Earth, igniting the hope that one day we may uncover living organisms in places we can scarcely imagine. Volcanic activity can also serve as a fascinating window into the past, revealing the geological processes that have shaped a planet over billions of years. When a planet experiences active volcanoes, it suggests that heat is still being generated deep within its core, a remnant of the same processes that shaped it during its formative stages. During this early period, the planet was a chaotic environment where intense heat and pressure led to the melting of minerals and the eventual separation of materials by density. This process formed the core, mantle, and crust that many terrestrial planets, including Earth, share today. The types of volcanic eruptions and the materials they produce can offer clues about a planet's composition and the conditions it experienced when it first formed. For instance, if a planet expels gases like sulfur and carbon dioxide, it might indicate a history of volcanic activity that reflects the planet's original ingredients. These clues provide essential insights into the planet's development, allowing scientists to trace its geological history and better understand the forces that have shaped its present state. In the grand scale of the cosmos, volcanic activity remains one of the most potent symbols of a planet's ongoing geological story, an ever-present reminder of the dynamic processes that have forged the worlds we explore today. Furthermore, studying the chemical signatures embedded within volcanic rocks offers an invaluable glimpse into the geological evolution of planets, providing critical insights into how a planet's crust has changed and developed over time. These chemical markers can serve as a detailed historical record, chronicling significant events such as the cooling of lava flows, the solidification of magma, and the gradual formation of surface features that shape the landforms we observe today. Volcanic activity, in its many forms, plays an essential role in revealing the dynamic processes occurring beneath the surface of a planet, particularly in the planet's mantle, the thick, underlying layer beneath the crust. Understanding how magma moves and interacts with the crust allows scientists to decipher important information about thermal gradients, essentially, the temperature changes occurring within the planet's interior and the forces driving tectonic movements. These insights into the planet's internal workings help researchers construct models of planetary evolution, which, when compared with the geological histories of other planets and moons, can illuminate the broader processes shaping planetary systems across the universe. When studying volcanic activity, scientists also gain a more refined understanding of the forces at play during the formation of rocky planets, shedding light on the dramatic transformation from molten masses to the solid, habitable worlds we explore today. Among the most intriguing worlds in our solar system is Neptune, a planet renowned for its dark, hypnotic storms. These storms, often striking with vivid blue hues against the backdrop of the planet's deep, swirling atmosphere, are unlike anything we observe on Earth. Neptune's frigid environment creates a unique setting for the formation of its storms, which are governed by extreme cold and high atmospheric pressure. This contrasts sharply with the warm, turbulent storms we are more familiar with on Earth. Here, powerful winds, some reaching unimaginable speeds, stir up clouds of methane and generate massive storm systems that can persist for long stretches of time, creating complex and dynamic atmospheric phenomena. The extraordinarily low temperatures on Neptune's surface result in conditions where gases in the atmosphere condense into ice particles. These ice particles contribute to the storm's shimmering, swirling patterns, adding to the planet's eerie, otherworldly aesthetic. As these storms erupt, they give rise to dark vortices, massive rotating features that resemble hurricanes, yet are fundamentally different in their composition and structure. Neptune's storms are shaped by an intricate dance between wind patterns, thermal contrasts, and the condensation of gases. This complex interplay reveals how even the most distant, frozen realms in our solar system exhibit extraordinary atmospheric behaviors that demand further study. The presence of cold conditions on a planet profoundly impacts its storm patterns, especially in regions where temperatures drop to extreme levels. To understand how this works, imagine the atmosphere as a vast ocean of air. In this ocean, temperature differences create movement. Colder air, being denser and heavier, tends to sink, while warmer air rises, carrying moisture with it. As the warm air ascends, it cools, and the moisture within it condenses, forming clouds. This process creates low-pressure systems where the warm air seeks to rise and escape, but is blocked by the dense, cold air below. The resulting contrast in temperature drives the formation of powerful winds that shape weather systems in dramatic ways. This phenomenon is akin to the waves that form on the surface of an ocean when energy disturbs the water. When cold and warm air masses collide, they generate spiraling winds, towering clouds, and intense weather events. Cold conditions further enhance a storm's ability to retain moisture, contributing to heavier precipitation as the rising warm air cools and condenses into rain or snow. On planets with extreme cold, this interaction of contrasting air masses can give rise to unique types of storms that do not occur on warmer planets. For example, in polar regions, the stability of cold, dense air can trap moisture, leading to the development of persistent storm systems that might evolve into massive blizzards or other powerful weather phenomena. These storms, heavily influenced by the planet's cold environment, combine the forces of wind, moisture, and temperature differentials, resulting in some of the most captivating and formidable atmospheric events in the galaxy. The dark, captivating appearances of storms on planets like Jupiter and Earth stem from a complex mix of atmospheric factors. Within the heart of these storms, towering clouds form due to powerful updrafts of warm, moist air rising from the surface. As the air ascends, it cools and condenses, forming dense layers of clouds. The droplets of water or ice within these clouds scatter sunlight, creating a bright, illuminated cloud top. However, as we peer deeper into the storm, the clouds become thicker and more opaque, blocking sunlight from penetrating. This gives rise to striking contrasts. The bright cloud tops stand in sharp relief against the deep shadows cast by the dense cloud layers beneath. Furthermore, the movement of energy within the storm, driven by temperature and pressure fluctuations, leads to dynamic shifts in the clouds. This constant motion can create darker regions within the storm as denser areas cast shadows, while lighter zones reflect sunlight. The resulting interplay of brightness and darkness is a mesmerizing visual display, underscoring the immense forces at work within the storm system. The presence of specific chemicals and particles within the atmosphere, such as ammonia, can also contribute to the storm's overall color, lending it a distinctive hue that sets it apart from storms on other planets. This spectacular visual phenomenon is not just beautiful, but also a manifestation of the enormous forces shaping the planet's atmosphere. On planets like Neptune, where the storms are influenced by both low temperatures and high pressure systems, the atmospheric behavior becomes even more extreme. In these frozen realms, storms develop in ways that challenge our conventional understanding of weather phenomena, revealing the diverse possibilities that exist within our solar system's planetary environments. On Neptune, the extreme cold of the atmosphere plays a critical role in shaping its storm systems. The atmosphere's low temperatures and high wind shear create conditions that allow powerful gusts of wind to sculpt the planet's icy surface. These gusts can reach speeds fast enough to reshape the landscape, eroding ice and altering surface features over time. While storms on Earth, Jupiter, and Mars have their own distinctive characteristics, Neptune's storms are particularly fascinating because of the sheer violence and intensity driven by its cold and dynamic atmosphere. In comparison to other storms in the solar system, those on Neptune are some of the most tempestuous and fleeting. Unlike Jupiter's gigantic cyclones, some of which can persist for centuries, Neptune's storms are more transient but no less intense. These storms are driven by Neptune's position at the outer reaches of the solar system, where its atmosphere is subject to a unique set of conditions that result in some of the fastest winds, recorded anywhere in our solar neighborhood. The scale and nature of Neptune's storms showcase just how varied the forces of weather can be across different planets, highlighting the dynamic and ever-changing nature of planetary atmospheres. However, on distant worlds, storms are not always composed of the familiar icy precipitation we associate with Earth's weather. Instead, these cosmic weather systems often take shape as massive clouds and gaseous compositions, their very nature shaped by the extreme environments in which they occur. These storms, though unique and fascinating in their own right, present challenges and phenomena that defy typical terrestrial understanding. The low temperatures and shifting wind patterns on frozen planets combine to create atmospheric dynamics that are strikingly different from those we experience on Earth. While the scale of these storms may not reach the terrifying grandeur of Jupiter's monumental Great Red Spot or the immense dust storms of Mars, they still provide a stunning glimpse into the varied and mysterious ways in which planetary atmospheres behave. These storms help illustrate the incredible diversity of space weather, shedding light on how each planetary environment fosters its own distinct atmospheric conditions and storm systems. In the field of astronomy, a vast array of tools and techniques are employed to observe and study these visually captivating storms that unfold across the solar system and beyond. The primary method for studying these distant weather systems is through the use of advanced telescopes, both ground-based and space-bound, which allow scientists to peer into the atmospheres of distant planets. These powerful observatories capture incredibly detailed images of storm systems, offering an intimate look at their formation, evolution, and movement over time. By continuously monitoring these storms, astronomers can track how they grow, change, and even dissipate. The use of telescopes gives scientists invaluable insights into the behavior of atmospheric systems in environments far beyond our own. In addition to visual observations, astronomers also make use of spectrometry, a technique that analyzes the light emitted or absorbed by the storms. By studying the spectrum of light, an array of different wavelengths that range from visible light to infrared and beyond, researchers can uncover crucial information about the chemical makeup and physical properties of these storms. This method allows astronomers to understand the materials that fuel these storms, such as the gases and molecules present, and provides important clues about the conditions that sustain them. Spectrometry is one of the key tools in decoding the mysterious energy sources that power the weather systems on distant planets. Space missions are another critical resource in the study of planetary storms. Robotic probes launched on missions across the solar system carry instruments capable of directly flying through or orbiting storm systems, collecting data on atmospheric temperature, pressure, and gas composition. This first-hand data, often referred to as ground truth information, plays an essential role in validating and complementing the remote observations made by telescopes. Direct measurements allow scientists to better understand how storms form and evolve in real time, offering a deeper level of insight that distant observations alone cannot provide. Alongside telescopes and space missions, computer simulations and modeling have become indispensable tools in storm research. Scientists take the data collected from telescopes and probes and input it into complex models, which simulate storm behavior under various atmospheric conditions. These models provide valuable predictions about how storms might evolve, helping to explain phenomena that are otherwise too intricate to study purely through direct observation. By running these simulations, astronomers can test hypotheses, explore new variables, and develop a more thorough understanding of storm dynamics. Another key method employed by astronomers is the analysis of historical data. By comparing current storms with those observed in the past, researchers can identify patterns and trends that might not be immediately apparent. For instance, changes in storm intensity, duration, or frequency may be indicative of broader shifts in a planet's atmospheric behavior. This longitudinal approach helps scientists track how storm systems evolve over time, offering a dynamic view of how these weather patterns might change or intensify in the future. By weaving together data from past observations, modern research, and computer simulations, astronomers can piece together the intricate puzzle of planetary storm behavior, gaining a more comprehensive understanding of these alien weather systems. One of the most striking features of storms on distant planets is how they are influenced by the harsh, cold environments in which they occur. Unlike on Earth, where storms are driven by heat, water vapor, and the warming effects of the sun, the storms found on icy planets or moons must contend with extreme cold, which significantly alters their formation and persistence. On planets like Saturn, where the surrounding atmosphere is bitterly cold, the conditions are ripe for the formation of clouds, composed not of water vapor, but of ammonia and other gases that can remain in solid or liquid form at low temperatures. These chemical reactions proceed more slowly, allowing for the development of long-lasting, stable storms. The lack of solar warmth means that the storms do not dissipate quickly, as they might in warmer climates, but instead can persist for much longer periods. The cold also impacts the density and structure of storm clouds. Icy particles and frozen gases give these clouds a unique and often much denser composition compared to those on Earth. This results in storm systems that are more robust and capable of maintaining their integrity over extended periods. As winds swirl through these frigid environments, they often move at slower speeds than those on warmer planets, resulting in a more gradual dissipation of storms. Without the rapid heating and cooling cycles typical of warmer planets, these storms can last for weeks, months, or even years, creating a vastly different weather experience from what we are familiar with. The freezing temperatures also alter the way that chemical processes unfold within the storm systems themselves. In cold environments, chemical reactions occur at a much slower pace, making it more difficult for storms to build up energy as quickly as they would in the warmer conditions found on Earth. As a result, these storms often have different characteristics, such as slower winds, denser clouds, and more stable formations. This slow, steady development makes them fascinating subjects for scientists who are continuously amazed by how these frigid conditions can give rise to such complex, enduring weather systems. The intense cold of these environments doesn't just affect the storms in terms of their structure, it also changes the very way in which the storms interact with their surrounding environments. In particular, the presence of a planet's magnetic field can play a significant role in shaping storm behavior. The magnetic field, which arises from the movement of charged particles in a planet's core, acts like an invisible shield that channels energy through the atmosphere. In regions near a planet's poles where the magnetic field is most concentrated, this energy can have a profound effect on storm activity. The interaction between the planet's magnetic field and solar winds, streams of charged particles emitted by the sun, can lead to the creation of awe-inspiring auroras, where charged particles collide with atmospheric gases, releasing energy in the form of light. These displays, while visually spectacular, are often a sign of heightened storm activity in these regions. As solar winds push energy into the atmosphere, they can stir up local weather systems, leading to more intense or more frequent storms. The magnetic field's influence thus becomes a key factor in understanding how storms on other planets are not only shaped by their own internal dynamics, but also by the solar environment surrounding them. In the final analysis, the study of storms beyond Earth reveals an incredible diversity of weather systems, each with its own set of rules driven by unique combinations of chemical, physical, and magnetic processes. These storms, though often vastly different from those we know on Earth, offer invaluable insights into the dynamics of planetary atmospheres and the forces that shape them. As technology advances and our tools for observing and analyzing distant weather systems improve, the mysteries of these alien storms will continue to unfold, offering a deeper understanding of the complex and ever-changing nature of space weather. Moreover, storms have a unique ability to both influence and be influenced by the complex thermal dynamics of the polar regions. When a storm generates significant amounts of heat, it has the potential to alter the atmospheric pressure and flow patterns in ways that may push the boundaries of polar climates. This interplay can lead to dramatic shifts in ice coverage, affecting the planet's albedo, which is the reflectivity of the Earth's surface, as well as the overall climate system. The consequences of such interactions are profound, as they can trigger feedback loops that further exacerbate or mitigate the effects of global climate change. This intricate relationship between a planet's magnetic field, its polar regions, and storm systems creates a dynamic web of interactions, resulting in diverse and often extreme weather phenomena. Understanding these connections is crucial as it enhances our knowledge of planetary atmospheres and the forces that shape them, not only here on Earth, but also on other worlds. The study of storms in planetary atmospheres opens up a fascinating realm of discovery, shedding light on the forces that govern weather patterns on distant planets. When examining intense storms, particularly those found in planetary atmospheres, it becomes evident that they create environments rich in dynamic interactions and extreme conditions. These violent weather systems offer a natural laboratory for studying atmospheric science and particle physics. During such storms, vast amounts of energy are released, propelling particles through the atmosphere at extraordinary speeds and generating a series of fascinating phenomena. One of the most significant aspects of storms lies in their ability to generate electric fields. As winds howl through the atmosphere and collide with various particles, they can strip electrons from molecules, creating a state of plasma. This plasma, a mix of charged particles, profoundly alters the local physical environment. Understanding how these electric fields function and interact with particles can provide crucial insights into energy transfer mechanisms, as well as the creation of new compounds that not form under normal conditions. These insights not only enrich our understanding of storm dynamics, but also have broader implications for various fields of study, including chemistry and physics. Storms also play a pivotal role in influencing large-scale atmospheric circulation patterns. These patterns, in turn, affect cloud formation and precipitation, further shaping the global climate. Scientists closely monitor how factors like humidity, temperature variations, and other environmental conditions contribute to the development of storms. By studying these interactions, researchers gain a deeper understanding of the complexities of climate systems, which may lead to more accurate climate predictions. For particle science, intense storms can produce high-energy events such as lightning strikes, which are known to generate gamma rays. These emissions provide a rich source of data for researchers studying cosmic rays and high-energy particles, potentially offering new information about their origins and behavior. Furthermore, the turbulence and chaos within storms can stir aerosols and trace gases from the surface, lifting them into the upper atmosphere. This mixing process allows scientists to track the movement of pollutants, biological materials, and other substances, providing valuable insight into their roles in climate change and atmospheric chemistry. By analyzing atmospheric samples collected during or after these storms, researchers can identify changes in atmospheric composition, which can have profound implications for understanding global weather patterns. These changes may help to explain long-term shifts in the Earth's climate, offering a clearer picture of how our planet's atmosphere evolves over time. The violent dynamics of intense storms thus unveil a multitude of opportunities for scientific investigation, from particle interactions to the intricate workings of our atmosphere. Each storm tells a unique story of energy, chaos, and transformation, providing a glimpse into the forces that shape not only our planet but also the universe beyond. As scientists continue to explore the mysteries of planetary storms, they uncover layers of complexity that reveal how interconnected our world is with the forces of nature. When a new planet is discovered, it often sparks a flurry of myths and cultural interpretations, deeply shaped by human imagination and experience. Picture a vibrant world unlike our own, where swirling storms, unusual colors, and seemingly alien landscapes provoke stories about its origins. Cultures might envision this planet as a divine being or an otherworldly realm, drawing parallels to gods and cosmic entities from ancient myths. For instance, a planet with a tumultuous, storm-laden atmosphere might be seen as a symbol of wrath and chaos, serving as a cautionary tale about human hubris or disobedience. Conversely, a serene, idyllic world might symbolize hope and abundance, inspiring tales of a utopian paradise where all beings live in harmony. Such interpretations often reflect humanity's own struggles and aspirations, mirroring societal values and fears. Different cultures may create stories about the inhabitants of this new planet, Some might envision advanced civilizations, capable of harnessing extraordinary technologies and acting as guardians of ancient wisdom. Others could see the planet as a sanctuary for mystical creatures, representing our collective yearning to escape the mundane trials of everyday life. The characteristics of the planet, its position within the solar system, its alignment with celestial events, could further shape the myths surrounding it. These cosmic features might lead to beliefs that the planet's fate is intertwined with human destiny, influencing decisions, actions, or events on Earth. Moreover, the arrival of a new astronomical discovery often reignites spiritual and philosophical discussions, leading communities to view the cosmos with renewed reverence. Rituals and celebrations may emerge, driven by the human curiosity about our place in the vast universe. Thus, observing such a planet can inspire a rich tapestry of mythology, culture, and reflection, reminding us of our innate desire to understand the mysterious forces that shape our existence. It's through this deep connection with the cosmos that we seek to grasp the larger narrative of the universe and our role within it. The study of storms in our solar system, particularly on gas giants like Jupiter and Saturn, offers fascinating insights that challenge our current understanding of weather dynamics beyond Earth. Traditionally, weather phenomena have been associated with relatively familiar influences, such as solar radiation and atmospheric composition. However, the massive storms observed on planets like Jupiter and Saturn, with their immense size and longevity, force scientists to reconsider several aspects of atmospheric science. For example, the Great Red Spot on Jupiter, a colossal storm that has been raging for hundreds of years, perhaps much longer, challenges traditional weather models. Its persistence and scale defy expectations based on terrestrial weather patterns, which are typically temporary and much smaller in scope. This anomaly raises critical questions about how energy and materials are mixed within such vast systems and what underlying processes sustain the activity of these storms over such extended periods. As we continue to observe and study these massive planetary storms, we unlock new dimensions of knowledge about atmospheric processes that extend far beyond the boundaries of our own world. The mysteries they present continue to fuel scientific inquiry, offering endless possibilities for discovery in the realms of weather, physics, and planetary science. The dynamics of storms on distant gas giants are far from simple, as they are profoundly influenced by the deep atmospheres of these colossal planets. On Earth, we're accustomed to weather systems driven by solar radiation, where the sun's energy plays a critical role in creating weather patterns. However, when studying the atmospheres of gas giants, scientists are uncovering a whole new layer of complexity. The pressure, temperature, and composition in these planetary atmospheres can behave in ways that starkly contrast with what we observe here on Earth. What truly sets them apart, however, is the fact that internal heat derived from a planet's formation process, rather than sunlight, is a significant driver of these immense weather systems. This emerging revelation is challenging the long-standing belief that storms are predominantly fueled by solar heating. Through the use of advanced telescopes and spacecraft, scientists are beginning to peer deeper into these celestial storms, observing behaviors that defy conventional understanding. They are seeing that the interactions between different atmospheric layers often lead to unforeseen outcomes. For example, the way winds flow at incredibly high speeds and the role that substances like ammonia and other compounds play in the atmosphere contribute to a complex system that cannot be easily captured by traditional models of atmospheric circulation. What's fascinating is how these discoveries about other planets could ultimately deepen our understanding of our own Earth's weather systems. The study of extraterrestrial storms holds potential far beyond just understanding distant worlds. It could have implications for the way we think about Earth's changing climate. By observing the storm systems on gas giants, scientists are being prompted to rethink outdated theories about atmospheric dynamics and consider how these new insights might be applied to our own planet. This shift in perspective may help us tackle the ever-growing complexities of Earth's climate, which seems to be in constant flux. As research advances, what we learn about these extraterrestrial weather systems could offer us crucial clues about the forces that shape our own environment. The study of storms across the solar system isn't just a scientific pursuit. It represents an intricate dance of forces that continually reshapes our understanding of weather, atmosphere, and even planetary formation. Each storm observed, each layer of an alien atmosphere explored, opens up new possibilities and challenges for both scientists and the public alike. What we're learning is not just about the distant worlds themselves, but about the very forces that govern weather on any scale, be it on Earth or far beyond. Turning our attention to another aspect of space exploration, we arrive at the concept of ocean worlds, a notion that's both captivating and eerily mysterious in the context of deep space exploration. The idea of vast, dark oceans beneath thick atmospheres is a concept that both excites and terrifies in equal measure. Imagine a world where an ocean stretches endlessly beneath a thick, impenetrable atmosphere. As one descends deeper, the pressure increases exponentially, creating an environment so hostile it would be deadly to most life forms as we know them. With light fading into near total darkness at the ocean's depths, explorers would find themselves in an alien world, devoid of the familiar cues we take for granted on Earth. This environment isn't just inhospitable in terms of pressure, it's also psychologically overwhelming, evoking a sense of fear and isolation. The concept of such extreme isolation where one could be submerged in an alien ocean and cut off from the rest of the universe brings to mind a psychological terror unique to space exploration. The crushing pressures are terrifying enough, but the idea of facing this danger alone, in a place where no human has ever been, is a potent source of fear. As humans continue to venture deeper into the cosmos, the notion of being completely isolated in the abyss of an alien world taps into deep-seated anxieties, blending physical peril with the existential dread of isolation. On these ocean worlds, the possibilities of what might be lurking in the shadows only add to the eerie allure. Could there be creatures adapted to thrive in extreme conditions, waiting in the depths? These bioluminescent beings, invisible to the human eye, could be reminiscent of the deep-sea life forms we find on Earth. Only here, they would be entirely alien. The fear of the unknown intensifies as we consider the possibility of life forms operating outside our comprehension, organisms that may challenge everything we know about biology and evolution. This fear and wonder are heightened further by the very nature of the deep oceans themselves. On Earth, the ocean's depths are known to conceal not just mysteries, but dangers. From deep-sea creatures with strange adaptations to entire ecosystems that thrive in the absence of sunlight, these depths represent a frontier as vast and uncharted as space itself. Exploring these unknown realms could uncover phenomena that defy our current understanding, pushing the boundaries of both science and human imagination. Beyond the psychological terror, there is the undeniable allure of exploration. With each discovery, scientists uncover new ecosystems, new life forms, and new ways life can survive under the harshest conditions. On Earth, we have learned to appreciate the diversity of life that thrives in our own oceans, from bioluminescent creatures to the extremophiles that inhabit the depths of hydrothermal vents. But what could exist in the depths of oceans on moons like Europa, Enceladus, or Titan? These alien oceans are completely isolated from the sun's warmth, yet the forces of gravity and chemistry provide the necessary energy to sustain life in ways we might never have imagined. The pressure at the depths of these alien oceans differs dramatically from that experienced on Earth. On Earth, the further down you go in the ocean, the greater the pressure because of the sheer weight of the water above. However, the deep oceans of distant moons present an entirely different scenario. For example, Europa, one of Jupiter's moons, is covered by a thick shell of ice over a subsurface ocean. The pressure at its depths may be extreme, but the ice above changes the dynamics in ways we don't see on Earth. In contrast, the pressures beneath Titan's thick atmosphere are much higher, primarily due to the dense, nitrogen-rich atmosphere and the thick layers of liquid methane and ethane on its surface. These environments pose unique challenges for scientists who seek to understand the conditions that allow life to exist in such far-flung places. The variation in pressure, temperature, and atmospheric composition on these moons could result in vastly different forms of life than we're accustomed to on Earth. The unique environmental factors of each world tell a different story. influenced by gravitational forces, fluid dynamics, and the very nature of the materials involved. For scientists studying the depths of both Earth's oceans and alien worlds, each dive deeper into these environments reveals a rich tapestry of unknowns, encouraging a reconsideration of what constitutes a habitable world. As we continue to venture into these dark, alien seas, we may find not only new species, but entirely new ecosystems, offering glimpses into how life could evolve in the most extreme conditions. These discoveries not only add to our knowledge of life in the universe, but also serve as a reminder of how much of our own world remains unexplored, particularly in the deep, dark recesses of our own oceans. In the realm of space exploration, developing the technology to withstand such extreme pressures is no small feat. To build vehicles capable of surviving the intense forces encountered on alien worlds or in the deep ocean, scientists must understand the unique conditions they will face. This involves considering temperature fluctuations, radiation exposure, and most importantly, pressure variations. Materials are central to this challenge. Engineers invest substantial effort into identifying and creating materials that can endure these extreme pressures without failing. Metals, composites, and other advanced materials are tested and designed to provide the necessary strength while maintaining a lightweight structure. Weight is crucial, especially for space missions, as every ounce added requires more fuel, affecting mission efficiency. This balancing act of strength, weight, and durability is critical to developing the technology needed for future exploration. Alongside material innovation, the design of these vehicles is equally important. Engineers use advanced computational modeling to simulate the exact conditions these vessels will face, allowing them to optimize the vehicle's shape and structure. Unlike traditional designs, which may be vulnerable to external pressure, innovative shapes like spheres or cylinders are used. These shapes naturally distribute stress and resist crushing forces, providing a more reliable structure to withstand the extreme conditions they will encounter. In this ongoing endeavor, the development of specialized vehicles is a race against the unknown. As our understanding of extreme environments continues to grow, so too does our ability to create the tools necessary to explore the deepest corners of the universe, whether it be the dark depths of alien oceans or the unexplored recesses of our own planet. Every step in this process not only uncovers new scientific knowledge, but also brings us closer to unlocking the mysteries of the cosmos. Moreover, rigorous testing is not just a procedural step. It is a fundamental pillar of technological development that ensures the reliability of vehicles meant for extreme exploration. In order to withstand the harsh conditions of outer space or the unforgiving surfaces of distant planets, vehicles must undergo extensive simulations that replicate the most extreme environmental conditions imaginable. These tests, which subject vehicles to extreme temperatures, pressures, and even radiation exposure, help engineers identify potential weaknesses in the design and functionality of these machines. Through this process, adjustments can be made, fine-tuning each component so that when the time comes for a real-world mission, the technology is not only proven, but also fully capable of handling the unprecedented challenges it will face. In the early phases of exploration, the objective is clear: ensuring that the vehicles are equipped to deal with the complex and unpredictable conditions that await. These preparations are not just about function. They are about safety, reliability, and adaptability. If human ingenuity is to reach beyond Earth, these machines must be prepared to face the unknown with confidence. Part of this preparation involves integrating redundant systems into the vehicle design, adding an additional layer of security. Redundancy is the practice of including backup systems that can seamlessly take over if primary systems fail. This is especially crucial in exploration missions to uncharted territories, where the risks are higher and every contingency must be accounted for. With redundancy, there's a safety net that can ensure the success of the mission, even when things do not go as planned. The development of pressure-resistant vehicles for exploration involves a delicate and intricate balance. The combination of advanced materials, innovative design strategies, and rigorous testing culminates in a machine capable of withstanding the harshest conditions of space and other celestial bodies. But it doesn't stop there. Robust safety measures are built in to make sure that even in the face of the most extreme conditions, human life remains protected. Together, these elements forge the essential tools needed to push humanity's reach into the farthest frontiers of the universe. The technological prowess behind such vehicles is nothing short of remarkable, a testament to human ambition and resilience in the pursuit of discovery. Simultaneously, the exploration of our own planet's ocean floor holds equal importance in the broader scientific context. Detecting thermal vents and other geological features in the deep ocean is crucial, not only for scientific exploration but also for ecological understanding. Thermal vents, often found along mid-ocean ridges, release superheated water that is rich in minerals. This release comes from beneath the Earth's crust, unveiling the dynamic nature of our planet's geology and showcasing the intricate interaction between the ocean and the Earth's interior. These vents reveal much about tectonic plate movements, offering scientists valuable data to understand how Earth's surface is shaped and transformed over time. Beyond their geological importance, thermal vents are the cradle of unique ecosystems. These ecosystems thrive in extreme conditions that would be inhospitable to most life forms. Unlike organisms that rely on sunlight for energy, the life forms living near thermal vents survive through a process known as chemosynthesis. Instead of photosynthesis, which depends on sunlight, chemosynthetic organisms convert chemicals released by the vents into energy. This discovery challenges long-standing assumptions about the limits of life on Earth and has opened up possibilities for life in environments that were once thought to be inhospitable. In fact, such extreme habitats might exist on other planets or moons in our solar system, such as Europa or Enceladus, which are thought to harbor subsurface oceans beneath their icy crusts. This realization profoundly changes how scientists think about the potential for life beyond Earth. If life can exist in such extreme conditions here, could similar life forms thrive on other worlds? The study of these unique environments on Earth provides insights not only into the origins of life on our planet, but also into the fundamental conditions required for life to emerge elsewhere in the universe. By understanding the biological and chemical processes that occur around these thermal vents, researchers can refine their theories about the possibilities of extraterrestrial life. The knowledge gained from studying these ecosystems could shape future missions to distant worlds, guiding the search for life on moons like Europa or on exoplanets orbiting distant stars. The significance of detecting thermal vents goes beyond their role in understanding the geology and ecology of Earth. These features provide vital information that enhances our comprehension of Earth's geological processes, ecological systems, and even the origins of life itself. Furthermore, they act as a gateway to exploring extraterrestrial possibilities, offering a tantalizing glimpse into environments that might harbor life in distant parts of the universe. Beneath the ocean's surface, a complex and dynamic system of currents plays a crucial role in regulating the Earth's climate and supporting ecosystems. Imagine the ocean as a vast, multi-layered system where warm and cold waters continuously mix, creating a dynamic flow of energy. Winds at the ocean's surface initiate currents that stretch across vast distances, sometimes traveling thousands of miles. These currents, much like the rivers on land, transport warm water toward the poles and cold water toward the equator, influencing global weather patterns and climate in profound ways. Yet, beneath the surface, a different set of currents takes over, a system known as thermohaline circulation. Driven by differences in water temperature and salinity, this circulation is an essential mechanism that regulates the flow of heat across the planet. In simpler terms, water becomes denser when it is colder or saltier, causing it to sink to the depths of the ocean. As this cold, dense water sinks, warmer water rises to take its place, creating a global conveyor belt of ocean movement. This circulation system can take decades to complete a full cycle, yet it is fundamental to maintaining a balanced climate across the Earth and distributing heat evenly between the poles and the equator. These currents are not only important for regulating temperatures, they also play a critical role in cycling nutrients through the ocean. The mixing of water helps to bring nutrients from the depths to the surface, where they are essential for marine life to thrive. Without this process, marine ecosystems would struggle to survive and ocean health would deteriorate. Furthermore, the underwater topography, such as ridges, mountains, and the seafloor, also influences these currents. Just as wind is redirected by mountains on land, ocean currents are deflected by underwater features, creating eddies and whirlpools that enhance mixing and nutrient distribution. These interactions create a vibrant and dynamic system that supports the richness of marine life. The health of the ocean and the functioning of these currents extend far beyond the immediate coastal areas. In fact, they influence weather systems across the globe, reminding us that the ocean is not a static entity, but a vital and active component of the Earth's climate system. The interconnectedness of ocean dynamics with global weather patterns is a powerful reminder of how delicate the balance of life on Earth truly is. As we look to the stars, the study of ocean worlds like Europa and Enceladus, or even distant exoplanets with vast, deep oceans beneath icy crusts, transforms our perspective on the potential for life in space. These environments, which are rich in water, may host the necessary conditions for life as we understand it. Picture an ocean world where a thick layer of ice blankets a vast ocean below, much like the conditions found on Europa or Enceladus. Geothermal activity within these oceans can create warmth, which would provide the necessary energy for life, similar to the hydrothermal vents found deep in Earth's oceans. This discovery opens the possibility that life might exist not only in these distant worlds, but could be thriving under conditions we once thought to be impossible for life to flourish. Life on such planets could be diverse, complex, and resilient, just as it is in the extreme environments of Earth's deep oceans. The prospect of aquatic life on these far-off worlds challenges everything we know about the potential for life in the universe, offering exciting new possibilities for the future of exploration and discovery. The chemistry of oceans, whether they're terrestrial or found on distant worlds, holds a profound significance in our understanding of life itself. Earth's oceans are a cradle of life, teeming with nutrients and organic materials that sustain a diverse and vibrant ecosystem. These bodies of water, deep and wide, nurture a myriad of life forms, each one intricately linked by biochemical processes. And as we look beyond our planet, scientists speculate that the waters of distant worlds, alien oceans that may exist beneath frozen crusts or deep within the surface of moons and planets, could possess the same crucial elements necessary to foster life. The elements, the very building blocks of biochemistry, may be present, waiting for the right conditions to spark the processes we see in Earth's aquatic ecosystems. In these far-off worlds, life, if it exists, might not depend on sunlight as we know it. Earthly organisms rely heavily on the sun's energy to sustain life through photosynthesis and other processes. However, life in these distant places could thrive without such sunlight, relying on other sources of energy, possibly from the planet's core or through chemical reactions that mimic the life-sustaining processes we observe in deep-sea vents on Earth. This challenges our conventional views on habitability, pushing the boundaries of where and how life might exist. It suggests that if life can adapt to the frozen, dark, and distant oceans of other worlds, the search for life could be extended far beyond just Earth-like planets orbiting sun-like stars. Such a realization expands our understanding of what makes a planet or moon suitable for life. Instead of restricting our search to worlds with conditions identical to those of Earth, we must now consider the possibility that life could exist in environments much more extreme, different from our current expectations. These so-called ocean worlds, moons like Europa, Enceladus, or even distant exoplanets, are tantalizing candidates, offering clues that life could not only be resilient, but incredibly adaptive. They open the door to the possibility that life may be more widespread throughout the cosmos than we ever imagined, potentially flourishing in forms and environments previously thought inhospitable. At the same time, we cannot ignore the immense geological forces at play in these extreme environments. Deep beneath the surface of our own Earth, in the crushing depths of oceanic trenches or beneath miles of tectonic plates, tremendous pressures shape the planet's geological activity. Imagine the weight of countless layers of rock pressing down on a solid core. This crushing pressure doesn't simply exist as a force of nature. It is a defining factor in the geological processes that occur at these depths. The pressures are so great that they transform materials deep within the Earth's crust and mantle, changing the very nature of the rocks that make up our planet's foundation. As temperature and pressure increase, rocks become more ductile, capable of flowing rather than breaking. This change allows for the formation of magma, which may eventually rise to the surface, contributing to volcanic activity and shaping the landscape. Beneath the surface, the movement of tectonic plates adds another layer of complexity. When these plates shift and become trapped along fault lines, the stress can eventually overcome the strength of the rocks, resulting in sudden and violent slips, earthquakes that reshape the surface. These deep processes are critical for the recycling of materials. Subduction zones, where one tectonic plate slides beneath another, are responsible for creating deep oceanic trenches, and they also contribute to the formation of new materials by transforming surface rocks. These materials are carried back to the surface through volcanic activity, further reshaping the landscape and contributing to the planet's dynamic geological evolution. The interplay between gravity, pressure, temperature, and the movement of tectonic plates drives the ongoing transformation of the Earth's structure, resulting in a rich tapestry of ever-evolving features, from mountain ranges to ocean basins. But these immense forces don't just shape the geology of our planet. They play a pivotal role in the long-term transformation of the planet's structure, with tectonic activity creating both uplifting and subsiding areas that continue to define Earth's topography. This never-ending process, with its constant ebb and flow, serves as a reminder of how dynamic and fluid the planet's geology truly is. These deep, crushing forces, which exert their influence beneath the surface, are also crucial in maintaining the balance of Earth's ecosystems, as they regulate everything from the circulation of the oceans to the formation of continents. Adapting to such extreme environments where heat, pressure, and radiation are magnified offers valuable lessons for humanity. If life can survive in such harsh conditions, deep beneath ice-covered oceans or in places with extreme pressures, then perhaps we can also learn to survive in environments that challenge our current technological and biological limits. This idea is not just theoretical, it has real-world applications. As scientists and engineers strive to create technologies capable of surviving extreme conditions, such as high radiation, low gravity, and extreme temperatures, these innovations could hold the key to new advancements here on Earth. For instance, the development of life support systems capable of providing breathable air and clean water in environments with limited resources could revolutionize emergency response technologies and sustainability efforts in disaster-prone areas. Similarly, materials engineered to withstand the conditions of space, where temperatures can fluctuate dramatically and radiation levels soar, might lead to the creation of lighter, stronger materials for use in architecture and transportation on Earth. These advancements, born from the study of extreme environments on other planets, could ultimately improve the quality of life here at home, making us more resilient in the face of the challenges our own planet poses. The pursuit of life in the deep, dark oceans of distant worlds and the exploration of the crushing pressures that shape planetary geology are not just matters of scientific curiosity. They represent a fundamental reef life's potential, both beyond and here on Earth. As we push the limits of our exploration, we continue to learn about the immense resilience of life and the complex, interconnected processes that govern not only the functioning of our planet, but also the possibilities that lie in the vast, unknown reaches of the cosmos. Space exploration, driven by humanity's innate curiosity and desire to understand the cosmos, has led to a multitude of advancements that could profoundly impact life on Earth. As we push the boundaries of what's possible in space, the technologies developed to support missions, whether for energy production, waste recycling, or life support systems, are not only improving our capacity to explore, but could also inspire greener, more sustainable technologies here on Earth. For instance, methods devised to recycle waste in space habitats or generate energy more efficiently could be adapted to reduce environmental impact in urban settings. The innovations born out of space exploration, robotics, artificial intelligence, and autonomous systems are already finding practical applications in sectors such as agriculture, manufacturing, and healthcare. These developments illustrate how the challenges posed by space exploration not only expand our understanding of life beyond Earth, but also stimulate technological progress that can directly enhance the quality of life on our home planet. Beyond technological innovations, space exploration also forces us to reckon with the resilience and adaptability required to survive in the most extreme environments. The exploration of distant worlds offers new insights into how life might survive in harsh conditions, both on other planets and within Earth's own ecosystems. Space missions continuously push the boundaries of human ingenuity, leading to breakthroughs that are often transferred to fields such as medicine and environmental protection. In this way, the quest to understand the cosmos has profound implications, driving forward solutions to challenges here on Earth. One of the most compelling areas of comparison between Earth and the farthest reaches of our solar system is the role of water. Earth's oceans, unique in their richness of life, help regulate our climate and sustain ecosystems. They play an essential role in the planet's weather patterns and serve as a vital source of food and oxygen. Liquid water, as we know it, is critical for the survival of life. This fact becomes even more significant when we look at other bodies within our solar system that may also harbor water beneath their surfaces. Take Europa, one of Jupiter's moons, as an example. Beneath its thick, icy shell, scientists suspect there is an ocean kept warm by the gravitational forces of Jupiter and heat from the moon's core. This ocean may contain the necessary chemical ingredients and environmental conditions to support life, akin to the deep-sea ecosystems on Earth that thrive around hydrothermal vents. These vents support organisms that live without the need for sunlight, an adaptation that could also exist in Europa's hidden oceans. In fact, the more we explore these icy moons, the more we see the parallels to Earth's own undersea environments, where life flourishes despite the absence of sunlight. In addition to Europa, Saturn's moon Enceladus provides another intriguing comparison. The small moon regularly ejects plumes of water and ice into space, suggesting that beneath its frozen surface, an active ocean may exist. These geysers not only reveal clues about Enceladus's hidden ocean, but also hint at the possibility that microbial life could exist in these extreme conditions, much like organisms found in Earth's harshest environments. And then there's Mars, a planet that once had vast oceans covering much of its surface. Though these ancient bodies of water have long since dried up, the remnants of rivers, lake beds, and valley networks tell a story of a more temperate past. The evidence of liquid water on Mars raises exciting questions about the potential for life to have existed there, further linking the Martian history to the evolving story of Earth's oceans. Asteroids and comets, too, hold valuable clues to our understanding of water. These icy bodies, often seen as relics of the early solar system, may have played a crucial role in delivering water to Earth during its formative years. This revelation emphasizes that water is not an anomaly on Earth. It is a common thread that runs through the entire solar system. From the subsurface oceans on distant moons to the ancient lakes of Mars, water is central to the possibility of life beyond our planet. Earth's oceans, vibrant with life, provide a stark contrast to the more barren, frigid environments of distant worlds, but they also offer a comparative backdrop to understanding the role of water in supporting life in the universe. Jupiter, a giant planet engulfed by extreme radiation, presents another fascinating realm of study. Its atmosphere, wrapped in formidable layers of radiation, is driven by a magnetic field over 20 times stronger than Earth's. This powerful field traps charged particles from the solar wind, creating a tumultuous dance of energized particles. These particles spiral into the planet's atmosphere, where they collide with gases, resulting in stunning auroras at the poles. However, these auroras are not just beautiful. They are much more powerful than those on Earth. The radiation intensity generated by Jupiter's immense magnetic field is so potent that it poses a significant threat to any spacecraft that dares venture too close to the planet. The study of Jupiter's radiation environment and the broader challenges posed by space radiation reveals critical insights into the potential for life beyond Earth and the risks of human exploration. Radiation in space is a key concern for both biological life and future missions to distant planets. High-energy cosmic rays and solar radiation can have destructive effects on living organisms, breaking molecular bonds and causing cellular damage, which can lead to diseases like cancer and genetic mutations. On planets and moons with no protective magnetic field or atmosphere, such as Mars, radiation bombards the surface, making it an inhospitable environment for life as we know it. If life does exist there, it would likely be found in protected environments, such as underground, where radiation levels could be mitigated. For human exploration of other worlds, radiation is a serious concern. Long-duration missions to Mars, for example, will require habitats that can shield astronauts from harmful radiation while still allowing for activities outside. Space suits and transportation systems must be designed to absorb or deflect radiation, ensuring the safety of explorers as they push further into the cosmos. These radiation challenges not only affect the potential for life elsewhere in the universe, but also play a crucial role in determining the safety and feasibility of human missions to distant worlds. Earth's own auroras provide a mesmerizing glimpse into the interaction between our planet's magnetic field and the solar wind. These displays of light, typically seen in the polar regions, are a direct result of charged particles from the sun colliding with Earth's atmosphere. As these particles descend into the atmosphere, they interact with gases like oxygen and nitrogen, exciting the atoms and molecules within them. This process causes the gases to release energy in the form of light, creating the dazzling green, red, blue, and purple hues of the aurora borealis and aurora australis. The colors produced depend on the type of gas involved, with oxygen producing green and red colors, and nitrogen creating purples and blues. The position and movement of the auroras are influenced by both the Earth's magnetic field and solar activity. During periods of high solar activity, when the sun emits more charged particles, the auroras can become more intense and widespread. This intricate dance between cosmic forces and Earth's atmosphere not only offers a spectacular visual display, but also provides important insights into the dynamics of space weather and the planet's magnetic field. As Earth's magnetic field acts as a protective shield against harmful solar radiation, it underscores the critical role our planet's atmosphere plays in sustaining life. The charged particles in the solar wind could be harmful if they reach the Earth's surface without this protective shield. The auroras then serve as a constant reminder of the delicate balance between space and the atmosphere, illustrating the powerful forces at play in the universe and how our planet is uniquely protected from the harsh radiation that permeates space. When the solar wind encounters Earth's magnetic field, the interaction isn't as simple as the particles passing through unimpeded. Instead, a complex and dynamic relationship unfolds between the charged particles of the solar wind and the magnetic field surrounding our planet. As these high-energy particles approach Earth, they are not left to continue on their path. Instead, they are redirected by the magnetic field lines that emanate from the magnetic poles. These magnetic lines of force guide the particles along intricate paths, often steering them toward the poles themselves. The majority of the solar wind's radiation is successfully deflected, sparing Earth from the worst of its effects. However, some particles manage to slip past the magnetic shield, becoming entrapped by the planet's field and spiraling along these lines toward the polar regions. Here, something truly spectacular happens. As these energetic particles dive into the upper atmosphere, they collide with gas molecules, primarily oxygen and nitrogen. These collisions happen at high altitudes, and they transfer energy to the gas molecules, exciting them. As these molecules return to their normal stable state, they release the absorbed energy in the form of light. This process is the birth of the mesmerizing auroras, nature's own light show, visible as shimmering curtains of color across the polar skies. The color palette of these auroras varies, ranging from vivid greens to deep reds and purples, depending on the type of gas and the altitude at which the energetic collisions occur. Thus, the magnetic field does more than protect the planet from harmful solar radiation. It transforms a potential threat into one of the most breathtaking phenomena visible on Earth. The dance of particles and light serves as a stunning reminder of the complex interplay between the planet's protective defenses and the intense forces at work in the universe. However, while auroras are a testament to the beauty that results from this cosmic interaction, the radiation from the sun, known as solar radiation, can pose a significant threat to both human health and technological systems. The risk is especially pronounced for astronauts, who are exposed to much higher levels of radiation than people on Earth. The most concerning health effects of solar radiation exposure include damage to DNA, which can lead to an increased risk of cancer. Radiation also interferes with normal cellular functions, potentially resulting in radiation sickness. Symptoms of radiation sickness include nausea, weakness, and skin burns, which can range in severity depending on the level of exposure. Beyond these immediate health risks, the long-term effects of space radiation are equally troubling. Astronauts who spend extended periods of time in space may experience accelerated aging of tissues, which can lead to issues such as vision problems and an increased likelihood of cardiovascular diseases. Studies have shown that exposure to cosmic rays, high-energy particles that come from outside the solar system, can penetrate the human body and interact with internal organs, heightening the risk of cancer and other illnesses long after the exposure itself. For technology in space, the risks of radiation are no less significant. Satellites, spacecraft, and other spacebound equipment are vulnerable to damage from radiation. Solar and cosmic radiation can interfere with electronic components, leading to malfunctions or even total failures. This is especially concerning for critical systems such as communication networks, navigation tools, and scientific instruments. To mitigate these risks, engineers design systems with radiation shielding and employ materials that can withstand or recover from radiation damage. Despite these protective measures, however, the radiation risks can never be entirely eliminated. These challenges necessitate careful planning and innovative solutions to ensure the safety of astronauts and the reliability of technology as humanity continues to explore the cosmos. Yet, beyond the immediate risks, the study of auroras offers a unique window into understanding space weather and its broader implications. Auroras are not merely beautiful displays of light. They are also powerful tools for scientists studying the relationship between the sun's solar wind and the Earth's magnetic field. By studying auroras, researchers can gain valuable insights into space weather phenomena, such as geomagnetic storms. These storms occur when the solar wind disturbs the magnetic field, energizing particles in the upper atmosphere. As these particles are funneled along magnetic lines toward the poles, they create the dazzling light shows we associate with auroras. Such observations help scientists better understand the dynamics of space weather, providing insights into how solar activity can affect Earth's environment and technologies. Auroras can also reveal crucial information about the strength and structure of Earth's radiation belts, zones where charged particles are trapped by the magnetic field. By examining how solar conditions influence the intensity and location of auroras, researchers can develop more accurate models of radiation belt behavior. This is vital because fluctuations in space weather can have significant effects on satellite operations, communication networks, and even power grids on Earth. The study of auroras, therefore, is not just about appreciating their beauty. It is about gaining a deeper understanding of the natural forces that shape our planet and its surroundings. This knowledge is crucial for improving our ability to predict and mitigate the impact of solar storms on human activities and technology. With a growing reliance on satellite-based systems for communications, navigation, and weather forecasting, the ability to predict space weather is becoming increasingly important for safeguarding technological infrastructure and ensuring the safety of astronauts in deep space. When we consider the challenges faced by researchers and engineers working to observe distant planets and space phenomena, we realize that the task is fraught with technical complexities. The vast distances between Earth and other planets in the solar system, or even further, to distant stars, pose a significant challenge for observation. Just as sound becomes faint as we move farther from its source, light and other forms of electromagnetic radiation weaken over vast distances. This diminishes the amount of data that can be gathered by telescopes and spacecraft. As spacecraft venture farther from Earth, the faintness of signals becomes an increasingly important issue. To combat this, astronomers and engineers rely on highly sensitive instruments that can detect even the faintest signals from distant sources. However, gathering clear and accurate data involves much more than just sensitivity. Telescopes, whether they are on the ground or in orbit, rely on advanced optics and technologies that focus light and filter out background noise. Each planet is unique, with varying atmospheric compositions, brightness levels, and physical characteristics, meaning that instruments must be tailored to adapt to these differences in order to provide accurate measurements. Ground-based telescopes, in particular, face additional challenges due to atmospheric interference. The Earth's atmosphere, filled with turbulent air and varying weather conditions, can distort the light coming from distant celestial objects. This phenomenon is known as atmospheric distortion, and it can cause celestial objects to appear blurry. To counteract this, astronomers use adaptive optics, a technology that allows telescopes to adjust in real time to compensate for these distortions, ensuring sharper and more accurate images. Another significant hurdle is the delay in radio signals from distant planets or spacecraft. Data transmitted from these distant objects takes time to travel across space and reach Earth. The delay can be particularly problematic when real-time data analysis is needed, as mission teams on Earth must find ways to make decisions and adjust plans based on information that is not immediately available. This time lag necessitates the development of predictive models and autonomous decision-making systems to support the success of space missions. In conclusion, the exploration of space presents both awe-inspiring discoveries and considerable challenges. The interplay between the solar wind, Earth's magnetic field, and the mesmerizing auroras is just one of the many phenomena that reveal the complexity of our universe. At the same time, the dangers posed by solar radiation remind us of the fragile nature of both human health and technological infrastructure in space. As we continue to explore the cosmos, the need for innovative solutions to address these challenges becomes ever more pressing, pushing the boundaries of science and engineering to new heights. Navigating the extremes of space presents one of the most daunting challenges for human exploration. As spacecraft venture into the vastness of the cosmos, they face an array of obstacles that can endanger their mission, ranging from high radiation zones to the extreme temperatures and vacuum of space. These harsh conditions necessitate spacecraft that are designed to endure the unrelenting forces of the universe, demanding materials capable of withstanding the worst that space can throw at them. The engineering behind these robust designs is far from simple. It not only increases the cost of building spacecraft, but also complicates every stage of their development. Maintaining the functionality of such vehicles over long durations requires cutting-edge technologies and innovative solutions. Systems that must stand the test of time in environments where failure is not an option. One of the most pressing challenges in space exploration is the study of distant planets and celestial bodies. Observing these far-off worlds requires instruments that are sensitive enough to capture data despite the immense distances involved. But even the most advanced technology can fall victim to interference from atmospheres, cosmic dust, and communication delays. Furthermore, the extreme conditions of space itself, such as fluctuating radiation and temperature extremes, can drastically affect the instrument's ability to function properly. Each of these obstacles necessitates inventive solutions, applying the fundamental principles of physics and astronomy in new and creative ways. As complex as the task is, it remains one of the most thrilling aspects of space exploration. The constant push to understand the universe in ways that were once thought impossible. Among the most captivating phenomena observed in space are the auroras, those breathtaking displays of light that swirl across the skies at the polar regions of various planets, including Earth. These luminous, shifting bands of color have long been a source of wonder and awe for observers, both ancient and modern. In the past, these brilliant lights were often seen as something otherworldly, a cosmic mystery that sparked the imagination. For early civilizations, the appearance of auroras was not merely a natural event, it was seen as a sign of deeper forces at play. Many ancient peoples believed that the eerie glow in the sky served as a bridge between the earthly realm and the divine, a signal from the gods or perhaps the spirits of ancestors. These mystical interpretations did not stop at awe and wonder. In many cultures, auroras became woven into the very fabric of folklore. Some believed that the lights represented a warning, an omen of impending change or even conflict. Others saw them as a reminder of the unpredictable power of nature, something that demanded respect. This folklore often carried cautionary tales, emphasizing that those who disrespected nature's wonders or ignored the signs from the cosmos might face dire consequences. Across various traditions, the aurora became not only a symbol of beauty, but also a metaphor for the balance between human actions and the broader universe. As these stories passed down through generations, they solidified the idea that human lives are intricately linked to the celestial forces above. The aurora, in all its dazzling beauty, became a symbol of this relationship, urging humanity to tread carefully in its interactions with the natural world. Through its captivating light, the aurora serves as both an aesthetic wonder and a reminder of the vast, powerful forces that shape our existence. When considering the nature of space and the challenges posed by radiation, one might be drawn to the planet's relationship with cosmic phenomena. The planet's environment can be compared to several extreme cosmic phenomena that share similar characteristics, particularly those around neutron stars, pulsars, and black holes. Neutron stars, for example, are the remnants of massive stars that have undergone supernova explosions. These stellar remnants are incredibly dense, with gravity so strong that it warps space and time itself. The intense rotation of these stars generates beams of electromagnetic radiation that sweep across the galaxy like a lighthouse, creating a cosmic spotlight. A planet within the radiation field of such a star would be bombarded with high-energy particles, much like the environment surrounding the pulsar. Similarly, supermassive black holes, located at the centers of galaxies, exert an immense gravitational pull on their surroundings. As matter is pulled into the black hole's singularity, it heats up and emits high levels of radiation. This radiation is so intense that it can alter the properties of nearby planetary atmospheres, much like the radiation surrounding a neutron star. In these environments, the forces at play can sterilize a planet's surface, making it unlikely to harbor any form of life. The powerful radiation belts formed around these objects can also alter the physical characteristics of a planet, making it inhospitable to the conditions we associate with life. Even within our own solar system, we can observe extreme radiation environments. Take, for instance, Jupiter's radiation belts. The planet's immense magnetic field traps charged particles, forming highly concentrated zones of radiation around it. These radiation zones present significant challenges for any moon or object in its vicinity, much like the extreme radiation found near distant stars and black holes. These examples highlight the profound effects that radiation can have on planetary environments, offering a glimpse into the conditions that make some regions of space hostile to life. The study of extreme planetary environments greatly enriches our understanding of the cosmos and its diversity. Imagine a planet situated so close to its star that the temperatures rise to levels capable of incinerating almost anything we know of on Earth. Such extreme conditions force scientists to rethink everything we know about planetary formation and survival. Planets in these close orbits often have atmospheres that behave in ways that are completely foreign to our experiences. These atmospheres, scorched by the relentless heat of their parent stars, can feature clouds composed of minerals or thick, smog-like layers that obscure any clear view of the planet's surface. The study of these atmospheres provides invaluable insight into how energy from a star can shape a planet's climate and even foster weather patterns unlike anything we encounter on Earth. The study of planets subjected to extreme gravitational forces further expands our understanding of how these conditions affect habitability. Gravity plays a crucial role in shaping a planet's atmosphere, weather systems, and even its ability to support life. By analyzing the structural integrity of planets under intense gravitational stresses, Scientists are able to make educated guesses about whether life, or the building blocks necessary for life, could exist there. This research also allows astronomers to refine models of planetary formation, shedding light on the many factors that contribute to a planet's development. Each new discovery of an extreme planet, whether it's one with a scorching atmosphere, intense radiation, or crushing gravity, serves as a test case for our theories about planetary evolution and habitability. These planets act as laboratories where scientists can test their hypotheses about how different environments might support or inhibit life. As our understanding deepens, so too does our ability to refine our definitions of what constitutes a habitable world. With every new discovery, we move closer to understanding the full spectrum of planetary diversity and the possibilities for life beyond our solar system. These extreme planets not only broaden our understanding of the universe, but challenge our perceptions of what makes a world truly livable. The cosmos, as we continue to explore it, is more dynamic and full of wonder than we ever could have imagined.